don't get you over here and see and address to us what we should go ahead with the next future line of action with respect to research and also capacity building. So before I end, I would like to briefly introduce the participants, very briefly about you, your name, and from which organizations you are, because we don't have much time. We have the guest of the speaker here today. He has to leave for some time. So very soon, quickly, if you can start with the participant, maybe with Rajna ma'am, please. If you can give me a mic. Yeah.
Good morning, everyone. So am I audible here? Okay. Good morning, everyone. Myself, Vignesh, senior scientist from Division of Genetics of IAR. Thank you.
Good morning, everybody. My name is Dr. Rajna. I'm scientist at Division of Entomology, IRA. I'm Sri from Indian Institute of Maize Research, working in plant biology.
I'm Surya. I am from IIT. I'm doing JRF.
Good morning, everyone. My name is Shubhika. I am currently pursuing PhD from GB Pant University. Thank you.
Hello. Good morning, respected dignitaries. My name is Gauri Ranjan. I'm from Manipur. Currently, I'm pursuing my PhD at the Department of Agronomy from IIT Raipur. Thank you. Good morning to everyone. My name is Jarima Sohan and I am currently pursuing my PhD from CSK Himachal Pradesh, Krishi Vishwavidyalaya, Panipur.
Good morning.
Good morning, everyone. I am pursuing my PhD from Soil Science Division, ICAR.
Good morning, everyone. I'm Gayatri J, PhD scholar from Division of Environment Science, IAR.
Good morning. My name is Shivani Ranjan. I am from Dr. RPC Pusa, currently pursuing PhD, and I am in second year.
Good morning, everyone. My name is Sumit Saw. Currently, I am pursuing PhD from Dr. RPC Pusa, Bihar.
Good morning, everyone. Good morning, sir. My name is Sharon. I am pursuing second MSc from Division of Agricultural Physics, IRA, New Delhi.
Good morning, everyone. My name is Samuel Naik. I am from MSc second year from IASRI.
Good morning, everyone. My name is Vidya Madri. I am from MSc Entomology, IRA, New Delhi.
Good morning, everyone. My name is Venkatesh. I am currently pursuing in-service PhD in Division of Entomology. My place of working at ICR, Central Agroforestry Research Institute, Jhansi.
Good morning, everyone. My name is Rajesh. I am pursuing Masters from Division of Entomology, IRA, New Delhi.
Good morning, everyone. This is Vikas Dugesar from Banaras Hindu University.
Good morning, everyone. My name is Gopal Zado. I am from Akola. Currently pursuing MTech from Dr. PDQ Akola.
Good morning, everyone. Myself, Anurag Singh Suman, pursuing PhD in Department of Soil Science from Buyat, Banda.
Good morning, everyone. My name is Vineet Dher, pursuing PhD Agronomy from CSUT Kanpur.
Good morning, everyone. Myself, Sagar Karande from Maharashtra, MPQ Maharashtra. Thank you.
Good morning to everyone. Myself, Chinmay Kumar Sahu. I am from Pantnagar. I am pursuing my PhD in Department of Agrometeorology.
This is Tejashwari. I'm a remote sensing research fellow working with Vasan and RRA, focusing on agriculture in rainfed areas, India.
Good morning, everyone. I am Sital Kumar from Bihar, currently pursuing PhD from IIT, New Delhi.
Good morning, everyone. My name is Deepak Kumar Meena. I am from Kota, Rajasthan, and currently I am pursuing PhD in Division of Agronomy from IRA, New Delhi.
Good morning, everyone. My name is Dr. Ravin Suchan. I am working at Teaching Assistant Department of Soil and Agriculture Chemistry, CSUT Kanpur.
Good morning, everyone. My name is Suman.
I am pursuing MSc in Agriculture Physics Division in IRI, New Delhi.
Good morning, everyone. My name is Abhudip Sarkar, currently passing PhD in Division of Agricultural Physics.
Good morning, everyone. I am Chello Prakash from Agriculture Physics Division, the PhD, IRA.
Good morning, everyone. Myself, Nirmala Ruban, second PhD, Division of Genetics, IR.
Good morning, everyone. I'm Sukumar. I'm doing third PhD in Division of Genetics, IRA.
Good morning, everyone. Myself, Deepak Kumar from New Delhi and currently pursuing my master's from CU Imphal. Thank you.
Good morning, everyone. My name is Sharajit MC. I'm working as a scientist under the Center for Water Resources Development and Management under the Government of Kerala. Thank you.
Good morning, everyone. I am Dr. Rao, working as scientist, Division of Agriculture Engineering, IRI.
Good morning, all. Myself, Rajat, and I am pursuing PhD in the Department of Soil Science and Agriculture Chemistry from US, Bangalore.
Good morning, everyone. I am Vimla Shri, PhD scholar from Soil Science Department in University of Agricultural Sciences, Bangalore. Thank you.
Good morning, everyone. I am Supriya. I am from Patna, Bihar, and currently pursuing my PhD from Agronomy and DRI.
Good morning, everyone. I am Dr. Divya Vijayan, Assistant Professor Soil Science from Kerala Agriculture University.
Lot of demand with respect to young faculties and researchers. So we have something around 16 researchers who have joined with us physically over here. And many of they couldn't make it because of the delay in the train, and they are not able to make because they have to do their own sponsorship. So they are joining online. And we would, because of the time paucity, we are not able to introduce each and of everyone from the online who have participated. But we have many of the students and young researchers, they have joined with us. So thank you very much. I think your stay and this training will be very useful, and we'll try our best to make you more comfortable. Thank you.
Thank you very much, sir. I now request Dr. K.M. Manjaya, Nodal Officer, NAHEB, CAST, ICAR, to kindly brief this gathering about the genesis, your outlook, and expectations from the program. Sir.
Good morning to all of you. Most Honorable Chief Guest of today's function, Dr. Tilochan Mahapatra sir, with the former Secretary DARE and DGICR, and mentor to all of us. On the dais we have Dr. C. Vishwanathan, Joint Director Research, Dr. Ravinder Padaria, Joint Director Extension. Then we have Vinay Saigal, Head Agriculture Physics, Dr. R.N. Sahu, the coordinator of this program. I would like to brief about the NHEP CAST, and also we have a galaxy of participants, faculty members, and also the guest of honor, Dr. Prakash Chauhan, Director NRSC, ISRO Hyderabad. They are also available online to bless this training come workshop and also give their wisdom for the success of this program. The NHEP CAST, that is National Agricultural Higher Education Project, which is a World Bank funded project with the Association of Indian Council of Agriculture Research. It has been designed to strengthen the national agriculture education system in India with overall objective to provide more relevant and high quality education to agriculture university students. This program will promote efficiency and competitiveness through changes in working mechanism of agriculture universities, raising the teaching and research standards through improved research and teaching infrastructure, and enhanced faculty competency and commitments, and also making agriculture education more attractive to talented students. There are four key components under this NHEP, namely the Institutional Development Plan, Centers for Advanced Agriculture Sciences and Technology, that is what we have the cost. Then also ICR to support excellence in agriculture universities and ICR innovation grants to agriculture university. Out of this cost, we at IRI have received on the topic genomics assisted crop improvement and management, wherein we have to the objectives to fulfill, which are aimed at strengthening and enhancing the human resource in the area of genomics. Towards this, the institute has already developed the state-of-the-art facility laboratory that you must have visited or you will be using in your training program, providing training to students for different universities across the country, training of students in India and abroad also, and also conducting genomics research in 15 different disciplines. As I already said, the state-of-the-art facility that we call as the Discovery Center, which has been housing the equipments more than 7 crores. It consists of genomics lab, the drone remote sensing and big data analytics lab. On April 16th, 2021, in the presence of our Honorable Chief Guest, the Honorable Union Minister of Agriculture and Farmers Welfare, Rural Development and Panchayati Raj, Government of India, Sri Narendra Singh Tomar sir inaugurated the Discovery Center through virtual mode. So that you are going to utilize for your training program, not only limiting to your stay here, but also beyond your completing the program. At the same time, you will be more concentrating on the genomics lab. In addition to that, we also have the drone remote sensing and big data analytics lab. This drone remote sensing and big data analytics lab, which houses drones with imaging sensors such as RGB, thermal, multispectral sensors for near real-time monitoring and reporting of plant growth and health. The institute has also developed indigenously a ground mobile platform called PUSA Pheno Mobile, which can be integrated with different sensors, flexible in speed, height and distance for automatic imaging of crops in the field. This technology will be complementary to high throughput phenotyping and precision monitoring of crop condition for smart agriculture. The phenomics and genomics big data analytics, the lab which is having 2 servers and 25 workstations. So with this kind of infrastructure, we are in a comfortable position to house you and also to impart the very informative, not only the theoretical part and also the practical aspect of the topics which are relevant to the training, that is airborne hyperspectral remote sensing for agriculture. So I'm sure you will be having a good time completing this training come workshop at this institute, which has been given so much to the green revolution, and there are many different aspects besides this training. Earlier we have conducted already 18 trainings around directly benefiting more than 1,000 students. Not only at IRI, our target is all the SAUs and all the universities which are across the country, besides other agriculture universities and also other than agriculture university, the national institutes as well. One of the important aspect is also the research, because it is a cost program. We have funded more than 100 students of IRI to work on the aspects related to genomics and its management. High impact journal publications, you will be seeing what our students have published and the kind of work they are still continuing. They are going to publish many such papers. And recently we have selected 22 students for short-term training spanning about 2 to 2.5 months into different world-class institutions having highest QS ranking standings. So it is all possible because from the beginning we have got the excellent support. Even for the initiation of this project, The Honorable Chief Guest was the mentor. It was been speeded up, implemented across the universities, and also subsequently the national directors, Dr. R.C. Agarwal sir, Dr. Anuradha Agarwal, national coordinator, and our director, Dr. A.K. Singh, all the joint directors and heads of the division. And besides that, the core faculty members, we are there in the team. Dr. Kumar, Dr. Burman, Dr. Alko Singh, all of them are putting a lot of effort in making this program a grand success. I thank each one of you, and particularly those who are present physically and also joined online for this inaugural function. Thank you very much.
Thank you, sir, for enlightening us with the program objectives and vision. I now request Dr. Prakash Chauhan, Director, NRSC ISRO, Hyderabad, who have joined us today virtually for his introductory remarks.
खूबसूरत होता पाइप हो जाए बाला को थोड़ी जेल होती है जेल सबके लिए लगा पिंपल्स रिंकल्स मिटाए ये लिखा हुआ है सुबह स्नान करके इसने पहले चेहरे पे लगा छोड़ दे
हेलो
बालों की समस्या जैसे बालों का झड़ना बालों का बढ़ना
प्लीज अनम्यूट
पहले पता नहीं लिखा है अगर बाल तो झड़ करने हाँ सर
Sir, we are not able to hear you. Sir, we are not able to hear you. Sir, unmute yourself. Sir, unmute yourself.
मर्द पाला जन्म में सूख गए
आपने यहाँ से म्यूट तो नहीं कर रखा है आ जाएंगे
I believe they are not talking.
Sir, please. Sorry. Sir, please unmute yourself. Please unmute yourself. Sir, please unmute yourself. We are not able to hear you.
रोकी वाला क्यों होने पास में रख लीजिए हैं तो क्यों लगे कुछ दूसरी होना
कुछ आवाज आ रही
ये प्यार का नगमा है गाड़ी में सेट करें
उनका स्क्रीन करो ना पिन करो
लगा लो आज तो लगा लो लगा लो रे आज कौन देते मिलो आज मिलो बहुत ज्यादा चेस्टेड जॉनसन
वहां से बार-बार सिंबल आ रही है फोन नहीं उठा
ऑनलाइन विद ल्यूरा मोजो की रबानी मैजिक
No, we are not able to hear you. Okay. 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 we can continue. Then meanwhile, once is ready, then we will. There is some problem from his side.
I now very humbly request Dr. C. Vishwanathan, Joint Director, IERI and PI, for his introductory remarks.
Very good morning to all of you. It is a great pleasure to welcome all of you for this training. My duty is to introduce our chief guest and guest of honor, the most respected Solution Mahapatra, teacher for excellence, researcher for excellence,
Introduce
no sentence. Secretary sir, I welcome you for this function. Dr. Raman Padaria, Joint Director Extension, Dr. Srigal, Head Division of Agriculture Physics, Dr. R.N. Sahu, the course director, and Dr. K.M. Manjaya, the nodal officer in HEP cost, Dr. Kumar, training organizer, and all the co-course coordinators, dear students and faculty who serve for this important training program. I welcome all of you on my own behalf and on behalf of the Director IRI to this Indian Agriculture Research Institute. So this training program was scheduled in 2020 due to COVID. That time it could not be organized, but it is heartening to know that large number of students and scientists are actively participating in this training, and more than 650 online, and then again more than 400 for the training workshop. So I welcome all of you, and this is indeed a very important program. And I have a pleasant duty to introduce our chief guest, Dr. Trilochan Mahapatra. Sir was born in 1962 in Katak, a small village, Karibal, and he did his BSc Agriculture from Odisha Agriculture University and Bhubaneswar. And then he has done his master's and PhD from this institute, and he did his PhD, all his PhD work in this very same building. Sir, we welcome you to your own home and the home institute. Dr. Mahapatra sir has joined as a scientist at Indian Agriculture Research Institute in 1992 in the Biotechnology Center, and there he worked on various aspects of genomics. Indeed, he is the first person to work on the molecular genetics and molecular marker in the country, and he has developed a pool of human resource who has expertise in this area. The first genetic linkage map of Brassica he has prepared, and then he has contributed immensely to the development of genome sequencing of all the genomes like rice genome, tomato genome, pearl millet genome, PGNP genome, and other genomes where in India contributed extensively. At NRCPP, he led a mega program called as Anil Mining and Bioprospecting of Genes. So this project, 36 different institutes were involved, cutting across the crop science, animal science, fisheries, all the institute. It was one of the very important program which was conceived long back, and which has brought in many new genes and germplasm for use in the genetic improvement. He has also initiated and led the program on the EMS-induced mutagenesis on functional genomics of rice. This has led to several important products. Most important one is the herbicide tolerant mutant that was identified in this project, which is currently already used, and IRA has released two basmati rice varieties. This is very important for providing the direct seed-based cultivation and saving a lot of water. And in fact, the first marker-resisted bread basmati rice variety, or in the first marker-resisted bread basmati rice variety was released which is known as improved Pusa Basmati 1. Since then, several marker-resistant bread varieties have been released in the country, and in many of the cases, the developer has been trained at Professor Mahapatra's lab, which is a great honor and a great contribution to the country. And in case of other initiatives that any new cutting edge area, any technology comes, and he was the one he initiated first in the country, which include the use of the plant genomics or remote sensing for the crop improvement and crop management. That is precision agriculture. I remember when the sir was formulating the project in 2010, then he told that Dr. Sahu called Dr. Sahu and asked him to introduce this important area of hyperspectral remote sensing. And since then, he is guiding us in developing various programs. And today it is culminated in the National Network Program on Precision Agriculture. With reference to other major initiative, as then after that he has joined as director at National Rice Research Institute, Cuttack, where he started one of the mega programs at ICR, which is known as Incentivizing Research in Agriculture, consisting of 5 different components, which is addressing emerging issues of the agriculture and future research areas such as the C4 rice and the biological nitrogen fixation, which are very important basic research that he has initiated. And in addition to that, the low light tolerance and the semen sexing in cattle, and these programs are made a significant progress. Sir, we are also thankful to you for bringing the NAHP to the ICR, and this program has immensely benefited not only to the students of IRI and students of several agricultural universities, as Dr. Manjaya told, in different agriculture universities, either in the form of IDP or in the form of Center for Advanced Agricultural Technology. This program is providing skills to the faculty and students to make the agriculture education of India globally competitive. And in this, Dr. Manjaya talked about Discovery Center. In fact, when Dr. Mahapatra sir took over as director of IRI, he envisaged that IRI should have a Discovery Center, and where the students and faculty can carry out their original research work without limitation for any facility. So towards that direction, a small facility has been established at present on the genomics and the drone remote sensing. In addition to that, in his vision, there is another big center which is going to coming up, which is known as Agricultural Innovation Center, at the cost of about 100 crore, which is going to be the state-of-art facility for the entire country for doing basic and strategic research. So there are several achievements that he has made in the research and discovery, and in addition to that, he mentored large number of students. And wherever we go in the country, any agriculture universities or any basic universities, we can find his students. And he has been awarded with several awards and recognition. And it is a long list, and he has been also awarded like DSC from more than 15 different agriculture universities. As Sir told, I am not reading all the awards and honors, and I request all of you to see his CV for the paucity of time, and I am not reading all the award. And above all, he is very good, excellent teacher and researcher, that is, and a mentor. He has mentored several people, including myself, Dr. Sahu, and everybody sitting here. Sir, we are very grateful to you, and we welcome you for this important training. And I am sure your address will motivate all our young students and faculty, and those who are present here and joined online. Thank you very much, sir, for coming to this training. And if Dr. Chauhan is there, I think I take this opportunity to introduce Dr. Prakash Chauhan, currently the Director, National Remote Sensing Center at Hyderabad. Dr. Chauhan has obtained his postgraduate degree in applied geophysics from University of Roorkee. Now it is called as IIT Roorkee. He has obtained his PhD physics from Gujarat University, Ahmedabad. He has joined Indian Space Research Organization in 1991 at Ahmedabad as a scientist. Since then, he is working on various important space technology applications, including remote sensing technology for geoscience, atmospheric and ozonic process studies. And he has initiated research activities for planetary remote sensing at Space Application Center to study solar system objects, mainly Earth's mission for Moon and Mars through Indian planetary missions. He served as Group Director at Space Application Center, Ahmedabad for Biological and Planetary Science Group from 2014 to 2018. And then as Director, Indian Institute of Remote Sensing, Dehradun, after that, before joining as Director at NRSC, Hyderabad. His major important contribution includes the Earth observation applications, including development of algorithms for ozone color parameter retrieval, marine living resource assessment, aerial remote sensing for space and air quality monitoring, river and reservoir water level estimation using spaceborne altimeters, and coastal zone management, and several other discoveries. He also contributed the use of satellite remote sensing data for understanding the climate response of Himalayan cryosphere and air quality assessment from the space. In addition to that, he led the team of scientists for scientific analysis of data from Mars orbiter mission, and more recently his work on Chandrayaan-2 IRS spectroradiometer data resulted in unambiguous detection of water in the surface of Moon. His finding has conclusively established water molecules at different locations on the Moon. He is currently serving as chair of working group of various national and international bodies. And aptly, he has been awarded with several prestigious awards, which include Professor P.R. Pisharli Memory Award for the year 2004 by Indian Society of Remote Sensing, Hariom Ashram, Dr. Vikram Sarabhai Research Award for by the Physical Research Laboratory, and ISRO Merit Award by Indian Space Research Organization, and Satish Dhawan Award in Dehradun by 2016. He has published more than 150 peer-reviewed research papers, and he is Fellow of National Academy of Sciences, Allahabad, and Fellow of Indian Society of Remote Sensing and Indian Social Science Academy. Sir, I welcome you for this inaugural session, and thank you for joining us and agreeing to deliver a keynote address. Thank you, sir.
Thank you, sir, for introducing the dignitaries at the dais. I now once again request Dr. Prakash Chauhan, Director, NRSC ISRO Hyderabad, for his introductory remarks.
Dr. Sahu, can you hear me now? Are you able to hear? Yes. Okay, thank you. Sorry for this small initial hitch. Good morning to you all. The most respected chief guest of the day, Dr. Trilojan Mahapatra, former Secretary DARE and
Sir, you are still muted. Can you unmute yourself?
This one?
सबको unmute कर दो.
Can you hear right now? Are you able to hear?
Yes, sir. Yes, sir. We can hear you.
Hello? Can you hear me?
Can I hear?
No, they are not able to hear, I think.
Yes, yes, they are on.
Participants, can you hear?
Yes, yes.
हमारी तरफ से तो नहीं है हाँ
एक बार लॉग आउट करके उनको बोल दीजिए ना हमने इधर को कंप्यूटर उधर से कोई किसी की भेज देंगे
स्पीकर आपका स्पीकर नहीं नहीं हमारे तरफ से अभी तो म्यूट है नहीं नहीं म्यूट नहीं है वो हमारी तरफ से करो
हमारा तरफ से प्रॉब्लम नहीं उनका हमारा माइक चेंज मत कर लीजिए नहीं यहाँ तो दिखा रहे हैं नहीं इनका भी म्यूट है ना उनका माइक म्यूट है
I think there is some problem there.
Yes, yes. For participants, we are getting.
Yeah, participants are getting. I think there is some problem with,
Yes, yes, they're not getting for.
नहीं हमारा प्रॉब्लम नहीं है उनके तरफ से हो सकता है ना वो बोल रहा सोचने सुनाई दे रहा है ये तो बोल रहा है कि बाहर जाके कर सकते हैं हमारा आवाज उनके पास जा रहा है नहीं उनका आवाज आ रहा है क्या
हाँ जी सर
नहीं, participants are able to hear me, but you are not able to hear.
Now we are able to hear.
No, I'm.
So put this.
So, okay.
Now can you hear me?
Yes, sir.
Yes, sir. Abhi. But वो mute क्यों दिखा रहा है उनका? Mic? I don't know.
You please speak. I'll put my phone on sound mode.
Sir, it's causing too much echo, sir. It's causing too much echo.
Sir.
डॉक्टर साहू यूट्यूब पे कर लेते हैं इससे वो जा रहा है
ओके
ये उनको बोलिए सर वहां पे लगा दो
इको करेगा
ये तो इको बट ये यूट्यूब से लगा दिया
जी आवाज आ रहा है अभी
We are getting.
अच्छा, all of you getting? We are not getting that.
Yeah. They are making something.
We are not getting.
Yes, sir. Online we can hear you, but probably they can't.
YouTube से लगा के कर हाँ सर आ रहा है आवाज आ रहा है
Participant not getting, sir.
साहू जी यहाँ से सुना दे रहा Are you able to hear me now?
Yes.
Dr. Sahu, yeah, are you able to hear me now?
राहुल जी एक बार इसका ऑडियो खोलो ना इसका म्यूजिक ऑडियो बोला ये बढ़ाना बोलना
So can you speak, please? Chauhan sir, please, can you speak?
Yeah, Sahuji, good morning.
Yeah,
Are you
very much, sir. Yeah, you are audible now. Please go ahead.
Now we are audible, sir.
okay?
Thank you, thank you.
वो इसका स्पीकर बंद किया होता ना इन्होंने
टीवी का स्पीकर
हाँ अब जो भी आप बात करेंगे उसको लगा लेना
ठीक है
हाँ प्रॉब्लम मतलब टीवी का स्पीकर
Okay. Yeah. Good morning
Please
to
go
you
ahead.
all. I think, yeah, sorry for this inconvenience. Most respected chief guest of the function, Dr. Trilochan Mahapatra ji, former secretary, mayor and DG ICAR, director IARI, Dr. R.C. Agarwal, Dr. Ashok Kumar Singh, Dr. Vinay Kumar Sehgal, Dr. Ravi Sahu, and all the participants of this training program, which is being organized by ICAR Division of Agriculture Physics. Good morning to each one of you, and greetings from my side here from Hyderabad. In fact, I wanted to join this meeting in person, but because of some other issues, I could not come. So I apologize for that. However, now the technology has made things much easier, and we are able to get connected through online means. First and foremost, I would like to congratulate the Division of Agriculture Physics, IAI, for organizing this particular national training program on a very important topic of airborne hyperspectral remote sensing for agriculture applications. As many of you are aware, remote sensing technology has been playing a very vital role in various aspects of agriculture. And Government of India has also launched a very significant program called Digital Agriculture Initiative. So under the DSS initiative also, high resolution remote sensing data is now currently NRSC is providing to all the states for generating, farmers level field information in a geotagged manner, so that it can provide a foundation layer about the farming activity, and also to cater various aspects of digital agriculture in the country. Now, in that context, as many of you are aware, there is a strong need to monitor the cropping systems. There is also a strong need to monitor crop health-related parameters, biophysical crop-related parameters, soil-related, parameters, especially the soil nutrient status, as well as the soil moisture status. There are also issues related to pest and disease in the agriculture systems. All these aspects basically contribute to, the agriculture productivity at the farmers level. And now there is a big initiative by Government of India where they want to use earth observation and remote sensing technology as part of digital agriculture initiative, to provide vital information to the decision makers, or even at the farm level for doing the farm level management practices. In that context, a hyperspectral remote sensing, which has been around since almost now 1 or 2 decades in various forms, either from the airborne platform or from the space-based platform, and now more recently from UAV platform, has been very useful in providing information about the various aspects of biophysical parameters as well as biochemical parameters about various agricultural systems. ISRO has also launched various hyperspectral sensors from airborne as well as from the space-borne platforms. However, the aerial platform has become very popular once we have done a vital campaign with NASA and ISRO coming together. So NASA's Every Senji program or the NASA's Every Senji sensor was brought to India, and over certain experimental sites, large amount of airborne data, hyperspectral data starting from 400 nanometers to almost 3000 nanometers have been acquired, and large amount of experimental work has been done in terms of assessing various biophysical parameters about the crops, about the water quality, about geological structures, as well as about forest ecosystems, and even related to the soil parameterization. This particular experiment, which was conducted jointly both by ISRO, NASA, and many other partnered institutions, including IRI, Dr. Sahu, Dr. Sehgal, they all were involved, has provided a very good, database at a very high resolution, as well as handle to process this large volume every Senji data. Especially hyperspectral data has its own challenges in terms of processing the data and bringing out the useful information. So I am sure that this particular training program, which is being organized, and large amount of lectures, theoretical lectures in terms of understanding the fundamentals of hyperspectral remote sensing in terms of sensors technology, and most importantly, the processing and generating the information will be very, very useful for the stakeholders and all the participants, those who are participating in this training. This technology is now not only being used from different platforms like airborne platforms, UAV platforms, it's also being used at ground in terms of various other aspects related to agriculture systems, about food grading. One of the very important area where the IR-based hyperspectral technology is being used about the food grading, without doing any kind of sampling. For non-destructive sampling related aspects also, hyperspectral technology is becoming very important in terms of seed quality and seed grading also. Hyperspectral technology is being used at various industries. So I am sure that there are multiple use of this technologies from different platforms. And especially for agriculture systems, this is going to be very useful in terms of assessing the soil fitness and water content in the soil. So this data provides very useful information, and the farmers will get benefited by doing precision farming by the help of hyperspectral remote sensing inputs. So I will not take much time, and I am sure that this particular training program will provide a deep insight to the participants about various facets of hyperspectral remote sensing data acquisition, processing, and upcoming uh, applications in the agriculture area. I wish this particular training program a great success. I also would like to thank organizers especially. Thank you very much, sir.
Thank you so much, sir, for enlightening us about the research challenges, progress done so far in the field of airborne hyperspectral remote sensing. Now I request Dr. Anand Pataria, Joint Director Extension, IARI, to encourage us with his remarks. Sir.
Most admirable, respectable former secretary there and DG ICR, Joint Director Research, Dr. Viswanathanji, Head of Division, Dr. Binay, Coordinator of NHP, Dr. Manjiyaji, Coordinator of this training program, Dr. Ravi Sahu, and one of the significant contributors for this program, Dr. Om Prakashji, dear participants, faculty, and students of this division. It's really a great opportunity to be with you for a very important training program on remote sensing. As you know, the farming has taken a new shape, and smart agriculture is the call of the day. All the farmers require precision in management so that they can minimize their input and also maximize the output. And that can happen only through optimum use of all the resources. and I witnessed certain kinds of changes through the technology application, how the farmers have benefited. And long back, I was also associated with little bit contribution of remote sensing in assessing the water logging. At that time, Dr. Binay was at Ahmedabad Space Application Center, and we could get the benefit how to assess the exact area underwater logging. That gives a significant kind of input for the policy designer, how we can manage the water logging. Similarly, these kinds of knowledge what we gain from such kinds of training program, we should be always supported with the new knowledge and new skills, and for that inclusiveness is very important. I could see that more than 470 participants have joined. On the 25th there will be 400 more, almost 1,000 people associated with new skills. What is driving force is what kinds of acquisition of knowledge we are tempted to. That inquisitiveness we have to bring in. And I wish you all the best so that you can learn more and be also contributing to the society, because science and society has to go together. So wherever you do your research, output should be such that farmers and in general society can be benefited. All the best to all. Thank you.
Thank you, sir. I now very humbly request Dr. Trilochan Mahapatra, former Secretary DARE and DG ICR, to wish the workshop a success by motivating us.
जरूरी है ये Thank you very much. Very good morning to everybody. And Dr. Prakash Chauhan. And I don't see other dignitaries. Dr. A.K. Singh, Dr. Agrawal are not here. Dr. Vishwanathan, Joint Director, Research. Dr. Ravinder Padaria, Joint Director Extension, Dr. Binay Shegal, Head Agriculture Physics Division, Dr. Gaya, Nodal Officer Naheb, CAST IRI, Dr. Arin Sahu, you all know him, and all those who are present here from IRI, the faculty, the students, the trainees from various institutions, universities who are associated with this program, both training come workshop on airborne hyperspectral remote sensing for agriculture. At the outset, let me thank the organizers for inviting me, giving me this opportunity to be here before you, primarily to learn how things are happening and what is really the use of this powerful technology as we visualize. You have heard Dr. Chauhan, the expert in this area, explaining various applications of hyperspectral remote sensing and how best we can utilize in the field of agriculture. He did mention about digital agriculture, the drone-based remote sensing in particular, and how drones are being mainstreamed for various applications. During past 5-6 years, this field has really developed and developed at the exponential rate. In 2016, in 2015 when I joined as director of IRI. In fact, when I was asked what would be my priorities, that time I had said and spoken about it, that how one has to mainstream use of sensors, automation, remote sensing, and how best we can make use of these technologies in agriculture to enhance efficiency, reduce losses, and the process enhance productivity, save on time and resources, so on and so forth. Though I stayed here for a short while and then move on to Krishi Bhavan quickly, and there various activities which we initiated, they all today you see, some kind of results before us. The very fact that you all are sitting here, and the other day there was another program on aspects of gene editing and so on and so forth. In this very hall, it was also inaugurated. Genomics and applications. And this all through the National Agriculture Higher Education Project. And that we initiated with lots of efforts going into it and making it happen, implementing it in more than 50 to 53 the institutes, institutes, there are only a limited number, but a majority of them are state agriculture universities. And through this program, Dr. Manjaya was trying to explain, there are different sub-programs there. There is CAST and IDP and Institute Grant and various other sub-programs within each one of them. And IRI has this particular program, Center for Advanced Agriculture Science and Technology, which is called CAST. And this is one component of the National Agriculture Higher Education Project. And when we were actually discussing this issue with World Bank, that why it should be supported, and that is the argument which were provided to them very forcefully by us, that we would be building our human resource for tomorrow. Human resource, as you are as students, researchers, and also human resource in the form of trained faculty members. It is heartening to see that more than 670 faculty and students and researchers are attending this program online, in addition to the limited number who are here in this hall. This is one aspect, and there are various other things, the automation, use of sensors. The Rahuri University is elaborately implementing how sensors can be utilized for various purposes, for instance, irrigation, and various other things which are demonstrated. You go to different universities, how this NAHEP program has actually catalyzed the change in the form of human resource development in the arena of advanced genomics, of course, remote sensing and digital agriculture as a whole, the applications thereof, and use of sensors, and so on and so forth, which I visualized at that time when I was director. In fact, when I was director of Rice Research Institute, Cuttack, that time I started talking about it. And in fact, those days, before going to Cuttack, we were having this program of phenomics here, which was formulated and then, was driven by me for almost 2 years before I left in 2012. And Dr. Vishwanathan, came in to actually take it forward and establish this, world-class facility on phenomics, inaugurated by none other than our Honorable Prime Minister. So that shows the relevance and importance of all this that we are talking today, and we are going to learn in this training program. When I say this phenomics, and Dr. Vishwanathan will explain later, I believe, or his colleagues would explain, that when we were discussing what the different kinds of imaging, non-destructive imaging systems should be there in place, and hopefully you'll be able to see those and see how it works. We had long discussion with Limnatic, the company who was providing this, and they didn't have anything on hyperspectral. And it was actually the idea for Dr. Abu that we must have, the facility imaging using hyperspectral. And that is how this became a unique facility in the world. Nowhere at that point in time, in 2010-11, hyperspectral was, and was used as a method to image plants under stress, under various kinds of diseases or insects or whatever, the damages, the physical damage, or even physiological disorders. So all that one can detect using those. In fact, subsequently, whether it is near infrared, or visible, or whatever, fluorescence, and all facilities were built there, and it has a tremendous application. And subsequently, we thought probably field, phenotyping should be there, and Dr. Manjaya was mentioned about it. And globally also, you find, this area is moving very, very fast. So today, we want precision agriculture. We want agriculture to be saving on resources, whether it is water, fertilizer, pesticides, and so on and so forth. How do you do this? Unless you use technology. And that's probably is the reason why the drone-based agriculture is now mainstream. The Honorable Prime Minister launching Kisan Drone, and primarily for application of drones for application spraying of pesticides, liquid fertilizers, and so on and so forth. So I think this is the beginning. But the kind of startups which are coming up to provide solutions by using drones, that is something which is quite encouraging. The youngsters getting into it, providing services, drone services, for application of, say, pesticides or fertilizers. That is coming up in a big way. Of course, all these applications would require the use of the airborne devices, the drones, for imaging. Whether you are using the satellites for remote sensing. Today we talk of LIDAR, we talk of microwave, and microwave would be the ultimate. Despite you have clouds, you can still do remote sensing better. That's what I am told. So likewise, so if you have drones and you can fly over a area of 1,000 hectares or 2,000 hectares, and then see where is the application requirement with regard to pesticide, and where is the infestation, and there could be differential application of these chemicals, and in the process you save on cost, save on time, and so on and so forth. So you can do that, and that's the basic application which all you know. But more importantly, that so many of you are here, that shows the relevance of this particular area. My friends from genetics are here, and soil science are here, entomology are here. You name a subject, they're all here. And that means it cuts across disciplines. The applications of this particular technology cuts across disciplines. You can use these to screen the germplasm resource for various purposes. Disease resistance or reaction of plants to various diseases, pathogens or insects or so on and so forth. So you can do that. So given the wider application this technology has, and that's the reason why probably it has attracted so many trainees to be part of this particular training and workshop. And so I'm sure it would be quite rewarding if you do not move along with the developments, the frontiers as they move. I have seen how frontiers move during my lifetime. When we started, the way we were struggling to develop DNA markers in the form of RFLPs. And my friends who are here, they have seen when I used to teach here, these different marker systems. So how the marker systems developed and today where we are, and various other technologies. When we were planning for phenomics, that time probably at the global level, there are only few centers on phenomics. And today you have a large number of centers established. And similarly, when we planned for genomics, the rising of sequencing in late 1990s towards 2000, so new millennium was starting, and we were initiating RISE genome program without knowing much about the genomics, how it is to be done. And today, genomics is all around. Hundreds of genomes are sequenced, and plants, animals, insects, you name an organism. So the genomes are sequenced. So the frontiers are really advancing, and if we do not see it through, if we do not visualize, and that's the role of leaders, that's the role of leadership. And if you don't visualize and plan it out, then you will be left behind. In fact, this is the time to see what is that emerging at the horizon that we must be catching up very fast and delving deeper into it as a researcher, so that we are not really lagging behind. That is the piece of advice to you, Dr. Viswanathan and colleagues, that we must be actually having a very, I would say, keen eye to a group to actually keep hunting for such development which is happening globally, and then see what is that new thing which is coming up, and we must be planning now. Remote sensing, Dr. Saigal was telling, was used long before, but we left it, we forgot it. We could have been world leaders, but we didn't. So today we are just following and learning. So this is what is the problem, that how do we actually innovate and be developer of disruptive technologies ourselves, and giving something to the world, something new to the world. Can we really do this? My young minds are here, and you must innovate to give something new to the world. You should be the innovator, not a follower, a trainee. You should be the innovator. Why young minds cannot be innovators? Can we think in that direction? So unless we do that, we will be just following somebody who has developed the technology. So with that message, and urging you all to be innovator of tomorrow, to give something altogether new, discover something altogether different from what is existing. So can you really give that? So, and learn as much as possible. I'll not go into, there are a lot of topics and we are already late because of the technology. Technology is powerful, but technology at times really fails us. And, today I saw it's our own ignorance that failed us. It's not technology, but knowing the technology properly is also important. And if you do not know the technology properly, you will have wrong applications. And you may not be able to apply at all. So that's what our delay is, because we did not know how to apply. Our monitor was silent. So if monitor is silent, so obviously nothing comes there. So the big TV monitor was silent. So whatever you do, it falls flat. So that reveals what we must be thinking and what we must be doing. And that's a big lesson for all of us. So we see you all the very best. And, I believe these people who are here, they are also innovating in their own thinking process and how they are doing. You will see the drones. There's a big drone sitting here, and you will be demonstrated many things. Number of lectures are waiting, and enjoy the lectures. When I used to take classes, in the first class, I would say that if you are interested, then you stay in this class, because you have to sit for 2 hours and 3 hours sometimes. And if you're not interested, just go out and opt out of the course. And you have come out of interest. So this is very important. If you have interest, then you learn. You don't have interest, then nobody can make you learn, actually. So that is important point. And you have interest, and I believe you will learn, and you will be teachers of many, because that multiplies. Each one of you teaching another 100, and imagine how many will be taught in the arena of hyperspectral remote sensing. So that is the multiplier effect. And today, if you see molecular breeding, everybody wants to do and everybody is doing. This is the multiplier effect. What was done in early 90s, 91, 92, 93, every year you keep training hundreds of people, and that's the multiplier effect. So this multiplier effect, you will see in this particular field, and it is already there. So I'm sure with this program of NAHEP, the cast at IRI through this program, this is a brilliant effort. And Dr. Manjaya, Dr. Vishwanathan, Dr. Padaria, all of you. And of course, at the division level, physics has been a pioneer. And I believe, there was an attempt to close it down. There was an attempt to say, what is agriculture physics? So I had to defend myself and explaining what is agriculture physics and how relevant agriculture physics is. So there's a great deal of dismay at what I was telling with regard to defending agriculture physics as a subject in ARS and also as a discipline in agriculture. So you'll see this is only one application, and people used to think that only agriculture meteorology is agriculture physics, and there it ends. So it goes beyond. So even sensors part of agriculture physics, and nano is also part of agriculture physics. And unfortunately, we don't include all those here. And I believe we will modify the course curricula. Maybe you have already done to include all this. This is not just biophysics and a few parts of physics which is included here. So anyway, wish you a lot of things to talk about. So wish you all the very best. Wish the program a lot of good wishes for the program. Hopefully it would be a great learning experience for all of you. And thanks, Dr. Ravi Sahu Saab. Carry on. And you have that missionary zeal to deliver. And I believe that would be the ultimate to success. So thank you very much. Wish you all the very best.
Thank you so much, sir, for your guidance and continuous motivation to inspire us. Now I would request Dr. Vishwanathan sir to felicitate Dr. Trilochan Mahapatra sir with a in-house pot plant, which is an air purifier. I now request Dr. B.K. Sehgal to felicitate Dr. Vishwanathan sir, JDR, with a pot plant. Dr. R.N. Padaria, Dr. K.M. Manchaya, Now I request Dr. Rabi and Sahu to felicitate Dr. B.K. Sehgal, Head of Agricultural Physics, IER. Thank you. I request Dr. Rajiv Ranjan, Course Coordinator, ICAR, IERI, for a vote of thanks.
A very good morning to all of you. It is my great privilege to get opportunity to propose a formal vote of thanks on this occasion. I would like to thank all of the honorable delegates who blessed us with this with their presence. I, on behalf of organizing committee, convey deep regards and hearty thanks to our chief guest, Dr. Trilochan Mahapatra sir, former secretary there, DGICR, for accepting our invitation and being with us. Your thoughts have always truly inspired us, always, sir. I would like to extend my heartfelt gratitude to Dr. Prakash Chauhan, Director NRSC, for his gracious presence online. Despite his ill health and due to some technical glitch, there was some problem. And he, sir, will also deliver a lecture after this uh, tea session. I am also thankful to Dr. R.C. Agarwal, DDG Education, National Coordinator, NAHEP, and Dr. A.K. Singh, Director IRI, for his constant guidance. Although he is not here due to some urgent meeting, he is not. They are not present here. I am very much thankful to Dr. C. Viswanathan sir, Joint Director, Research and PI NAHEP, CAST IRI, for their constant guidance and support to shape the training this program. I am also very much thankful to Dr. R.N. Padaria, Joint Director Extension, for his presence and the small address which motivated us. My sincere thanks to Dr. K.M. Manjaya, Sir, Nodal Officer NAHEP, CAST, and Dr. N.D. Kumar, Principal Scientist, for their constant help and guidance in organizing this event. I would also like to thank to our head, Dr. Vinay Sagal sir, for his unhindered support and guidance throughout the chalking out the program. I am very much thankful to all of our faculty, colleagues, and non-teaching staff for their gracious presence here and who always stand with us during the program. I also thank to Dr. Amrendra Kumar, Head AKMU, for providing the uninterrupted internet connection. Dr. Manoj Khanna sir, for in charge OLU, for providing the floral decoration and bouquet. My sincere thanks to Dr. Rashri Barman sir for helping us in organizing this meeting in Zoom, and even this meeting is also live telecast on IRI YouTube channel. Thank you very much, sir. We are very much thankful to Head Environmental Science for providing this NRL auditorium, and in charge of this auditorium, Mr. Vinod Kumar, who always, when I called him, he always ready to support us. Thank you, Vinodji. Our special thanks to participants who came across the country to attend this program physically. I also thanks to the participants who are attending this program online for their overwhelming and their overwhelming response. As sir told that there are more than 650. Now it crossed 700 resistant in this program. I would like to thank Dr. D.K. Yadav, Administrative Officer, Plant Physiology, for taking care of the administrative and financial approval for the training in coordination. I am very much thankful to Dr. Raj Kumar, the course coordinator, for formulating the training courses and technical program, and he always help us in this training. Actually, we are immensely thankful to Dr. Arun Sahu, course coordinator, as myself and Dr. Raj Kumar. It is very learning experience for us, sir. And Dr. Sahu is the instrumental person to organizing this event and finalizing the things very meticulously. Thank you very much, sir. I also thankful the Photo Lab IRI for recording and covering this session. Thank you very much. At the end, I would like to take this opportunity to thank our nuclear counterpart, Dr. Raj Kumar, Dr. Salvi, Mr. Abhishek, Rahul, Manish, Om, Tarun, Rajit, Pratim, Vishal, Naveen, and other project staff who joined hands to organize this event. Thank you, all of you, for making this event successful. Now I invite you all for a cup of tea outside this auditorium. And before that, there will be a group photograph outside this NRL building. And the next session will start in after half an hour, 12:15. After 12 at 12:15. Thank you very much.
Hello, am I audible?
ये ना की वजह से वो हो रहा था, बेस हैवी हो रहा ना माइक्रोफोन की वजह से हो गया था, फोन में रह जाए।
अब सर नेक्स्ट सेशन में क्या होगा? ये सेम यही सेशन चलेगा?
नहीं, नेक्स्ट सेशन में प्रकाश चौहान वहां से प्रेजेंट करेंगे।
ऑनलाइन ये है जैसे अभी किया था, लेकिन आप
नहीं, मेरी तरफ से ओके, मेरी तरफ से कोई प्रॉब्लम
मैं
नहीं
देखता हूँ।
एक बार आके पहले चेक करें।
ऑडियो इसी से जाएगा, जो भी ऑडियो है ना, इससे नहीं, इससे सर, और यहाँ पे ऑडियंस को सुनाई देगा, ये सर।
हेलो, हेलो,
Hello, 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 hello.
Yeah, hello.
Hello, check, check.
Yeah, hello.
Hello, 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 hello. Hello, hello.
Hello, 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 hello,
Yes, sir. Can we leave the meeting now?
लेकिन मेहनत तो हमें करनी पड़ेगी। देख पहले तो मैं लोग कहते हैं बात बनना है नहीं, और फिर नहीं, फिर उसके बाद गई पक्का था। आदमी को तरह सोचने लगे भी नहीं कुछ ना है नहीं।
और नीचे जाओ
आवाज कहाँ से
So can we start now?
Yeah. Yeah, you are audible and you are visual also. You can share the screen and I think we can start with. So,
you see the presentation?
Yeah, I'm able to see your presentation.
Okay.
And thank you for accepting again the invitation to give a inaugural address on hyperspectral remote sensing, Earth and planetary surface. So we have around 60 plus participants, both students and young faculties who are physically present here, and many of them are online. So I think this introductory class will be giving them a wonderful exposure with respect to hyperspectral remote sensing, and which will be a kick point for us to start the program and give some kind of a practical demonstration and also different applications. Thank you again for sparing your time and kindly please go ahead with this.
Thank you, thank you, Dr. Sahu, for your inaugural comments, and welcome back to all the participants. When we are now starting the formal part of your training program, what I will try to give you, there will be very specific, detailed lectures in this training program. My purpose of this, initial presentation, just to give you an overview of hyperspectral remote sensing technology and its applications for various, application domains, both in terms of knowing more about surface processes at Earth in different ecosystem, studies, as well as, today beyond Earth also, in our solar system, we want to know more about our planetary neighbors like Moon and Mars. So how these remote sensing, hyperspectral remote sensing data sets are also being useful to know more about the planetary surfaces. Some idea I will give you, because ISRO has also launched some hyperspectral sensors on board some of its satellites like Chandrayaan and Chandrayaan-2, etc. So I will begin with just to introduce you this topic. I am not sure that how many of you have basic background of remote sensing, but just to tell you about what exactly we mean by remote sensing first, then we will come to multispectral and hyperspectral things. So remote sensing as such, is a method or a technology to know more about an object without coming in contact or in touch with it. See, a very simple example I can tell you that when you are in your home or when something is being cooked in the kitchen, you get a smell, even though you may be sitting far off, and you can find out that what exactly is being cooked in your home, simply because your nose is acting as a remote sensing instrument or a remote sensing sensor. Similarly, we see each other, whether we can feel the touch of each other or not, but we can see it because our eyes basically acts as a sensor which detects the reflected energy from the object. So these are all very simple examples which we can say that we are able to sense something in a remote manner, without coming in contact with this thing. But if I want to measure your, let us say, the temperature, or if you have a fever, then I need to touch your body to know that what is the body temperature you have. So that basically is not a kind of sensing which can be clubbed under remote sensing category. So same principles applies when we put some or some I think there is somebody speaking online. Can you please mute microphone, Suresh? Yeah. So when you put some sensors or some camera systems, or let us say on a satellite or on a aircraft or on a UAV, you are able to see the images of the Earth's surface in different resolutions. So we have a very high resolution imaging sensors, like we have around capability to detect, objects which are, let us say, 30 centimeters apart. We can also have sensors or cameras which can basically detect with things which are 10 meters apart or even kilometers apart. So depending on the kind of optics or kind of, camera system you are designing, your capability to do imaging of Earth's surface also changes. And see, typically, like your mobile phone camera, you can see in what we see visually, like a human eye can see. This is called the visible range imaging in a electromagnetic spectrum. But today, with sensor technology, it is also possible not only to see in the visible part of electromagnetic spectrum, but also to get idea about the surfaces in the near infrared part of electromagnetic spectrum, far infrared part of electromagnetic spectrum, and even we can sense the thermal signature or emitted energy from the Earth's surface or any other planetary surface. So if my sensor has some, let us say, some 5 or 10 such bands or channels through which I can see Earth's surface in different part of electromagnetic spectrum, such type of remote sensing is typically known as multispectral remote sensing. So ideally speaking, in a multispectral remote sensing sensors, we will have 5 to 10 bands through which we can, see the Earth's surface, which will have, each of these band will also have some finite bandwidth. Bandwidth can vary from, let us say, 770 to 400 or even less than that. So these discrete imaging in the part of electromagnetic spectrum is typically known as multispectral remote sensing. And many of you must have used Landsat data. Many of you must have used Sentinel data, even our LIST 3, LIST 4, and AWIFS data. All this type of imaging sensors, basically, they constitute what we call as the multispectral remote sensing sensors. And using this multispectral remote sensing the sensors, also, you can get a lot of information about, let us say, crops, let us say, about forest cover, about, the soils, as well as, let us say, water bodies, many things which are exposed on the Earth's surface, snow cover also. So this data conventionally is being used in remote sensing for various applications, even for crop classification, crop type estimation, crop area for different crops which are grown in different parts of the country. So today, using multispectral data, a lot of applications are being done. When we talk about hyperspectral, there is a difference between multi and hyper. Hyper means that you have number of channels. Instead of having only 5 or 6 bands or channels in an imaging sensor, you have hundreds of bands which are narrow, which basically detects energy in 5 to 10 nanometer interval, and they are continuously providing the information about the reflected part of the reflected energy from the object. So such type of sensing is conventionally known as hyperspectral remote sensing. And as you can see, this electromagnetic spectrum, the visible part is basically from 0.4 to, let us say, around 0.7 micron. But beyond this, in infrared and in the thermal part, there are large amount of atmospheric transmission windows. So you can have, continuous measurements all across this electromagnetic spectrum to produce what we call as the hyperspectral images. So this is an example that, you have, let us say, here I am showing some 6 such, images over a part of some area over Earth, which are basically individual bands. And when you can combine all of this information of hundreds of bands, you can create what we call as the data cube, or a card of, it's like a card of, pack of cards, or, the cards which you play, where 2 dimensions basically tells you about the horizontal and the vertical, variations, horizontal variations over the surface. But the third part or the third dimension will tell you about the spectral component around each pixel. That means what are the signatures of that particular pixel in question can be derived using these hyperspectral data sets in a very, very precise manner. So such type of sensing basically is typically known as the hyperspectral remote sensing. And that is what you will learn during this particular training program, that what are its applications, how to collect data and how to process data to get useful information. Now, there are various type of, hyperspectral sensing, strategies. So it is also known as in literature imaging spectroscopy, because you are generating the spectral signatures and then also creating an image of the surface. So you have a spectral range from 0.3 to 3 micron, and this is basically known as shortwave spectrum of electromagnetic broad spectrum. And then you also have the longer wavelengths, 5 to 50 micron, which basically gives you an idea about the emitted signal, not the reflected signal. Now, difference between the reflected signal and emitted signal is that when, let us say, sunlight is falling on any surface, it gets reflected, and then you can measure this reflected energy from 0.3 to 3 micron range very conveniently and generate hyperspectral image cube. But during the daytime, the sun's or solar energy is also basically getting absorbed by the surface, and then you can see sometime even summers, while sun is not there, still the objects are very warm. So they are warm because they have retained or absorbed the solar radiation, and then later on they are emitting this solar radiation. So like our scene that people are measuring temperature of the body by a thermal gun. So this thermal gun is sensing nothing but the emitted energy from our body or heat from our body. Same way, Earth also emits heat in these spectral range from 5 micron to 50 micron. In fact, it emits in another wavelengths also, but the reflected components during daytime dominates. But in this 5 to 50 micron range, it's all typically the emissive signal. So both in shortwave and long wave, you can have sensors depending on the detectors, and it also depends on what kind of information you want to derive. Then this hyperspectral data is also used for atmospheric sounding. That means atmosphere is a three-dimensional body. As we go from the surface of Earth, up to 100 kilometers, the atmosphere's expansion is. And meteorologists, basically, they want to know that how temperature and humidity is varying as a function of height. So if you want to do this type of information extraction, a typically instrument called the sounders, and these sounders also provide not only the two-dimensional information but also the vertical or the third dimension information about various parameters like humidity and temperature, etc. So these are all the three typical ways of generating hyperspectral information about the surfaces. Before going just basic physics, is important to understand that what is the basic fundamental or behind this reflective spectroscopy. It is not that everyone need to know the basic physics, but it is better to know that why we get this spectral signature. So as I told you, that most of the energy is basically reflected energy, but in certain wavelength region, different objects also do absorption of energy. And this absorption of energy is basically gives you a characteristic idea about the material in terms of its diagnostic absorption features or overtones, across the reflected or the emitted spectrum. So we will see examples of this. Don't get unduly worried about it. So let's say if many of you are agriculture scientists, you all may be aware about that leaves, they contain a pigment called chlorophyll A. And this pigment, chlorophyll A, basically if you do, the spectroscopy of this chlorophyll A pigment, you will find that it absorbs very strongly in the blue part of electromagnetic spectrum as well as in red part of electromagnetic spectrum, and then it reflects energy in the green part of electron. That's why the leaves traditionally they look much greener. because the blue and the red part of electromagnetic energy is absorbed by this particular pigment. And this kind of specific absorption by this pigment can be detected using this spectral or imaging spectroscopy through the process. Two broad physical, electronic as well as vibrational processes they occur, which basically reflects in the typical absorption features by different materials. So one classical absorption feature is produced through what we call as the electronic transitions. And these electronic transitions is nothing but change in the energy state of electron bound to atoms, while these electrons are getting excited by, let us say, the sun's energy. And they also, once they come back after the excitation, then also they basically provides another kind of information. It's called the vibrational transitions. So these type of transitions occurs for different materials at different wavelengths. Let us not get into too much of details of it. When the specific examples will come, I will try to explain you about both electronic and the vibrational transitions created by different type of materials in different part of electromagnetic spectrum. Now, this is a typical spectra which one measure from a sensor, let's say, for different type of leaves. This is typically for a agriculture, maybe a vegetative system. So you have on x-axis this wavelength from 400 nanometer going all the way up to 2500 nanometers. And on the y-axis is nothing but what is known as the reflected energy. Reflected energy is nothing but the ratio of incoming solar energy divided by the outgoing energy. So you can make measurements through of this incoming and outgoing energy through some instruments, and the ratio of this is basically known as the reflectivity or reflectance. So now, as you can see, there are different type of reflectance spectra are plotted for conifer leaves, for grass, for broad leaves, for some brushes, etc., etc. And then you can see that some of it, in case of, let's say, broad leaf spectrum or conifer leaf spectrum, as you go from 400 to, let us say, 500 nanometers or so, the absorption, the reflectance is very high compared to what you have in the red part of electromagnetic. And then suddenly, when you are into the NIR region, beyond 700 nanometers is the near infrared region, then you can see the reflectivity changes or the reflectance changes very dramatically. And this change of reflectance in leaves is typical, spectral signature of vegetative, surfaces, which gets very broadly captured in the IR region. And then you have leaf water, absorption features also, cellular scattering features also. Then the pigmentations which are present in the leaves, they also show up their classical absorption, like cellulose, lignin, and then related, chemistry, which also plays a role in different type of leaves. Then the water content in the leaf also basically gets, highlighted at around 1.5 micron and so. So that also is a very good signature about the water stress in the leaf systems, as well as this particular, enhancement in reflectance at near infrared is also known as red edge. So this red edge also gives an idea about the health of the leaves. And you can see that for the soils, etc., the reflectance spectra is very, very different compared to the leaves which are having green color, and the leaves which are basically which are not green or which has turned yellow, the reflectance spectra basically have more reflectivity in the yellow red region compared to the absorption by the green leaves caused in the red region. So using these classical spectral signatures, one can derive lot of information through some indices about the the vegetative systems, the species distribution, the water availability in the leaves, the kind of pigments which are present, some of the disease also, basically they also give some signatures in certain spectral regions. So those type of absorption or biochemical properties also can be derived using this type of complete spectral signature using this hyperspectral remote sensing data. But when you compare to this multispectral data, you get only part of this information. You don't get this continuous information. So that way, you also can miss a lot of absorption features, and then it is very difficult to get the complete diagnostics of biophysical and biochemical properties of the leaf surfaces when we have multispectral data sets. So this is the typical advantage of hyperspectral data compared to the multispectral data, that you can get information about the characteristics that absorption features which are specific to one particular biophysical or biochemical property. Now, as far as the level of spectral information is concerned, you have less information in panchromatic or multispectral data, but you have very high spectral information in the hyperspectral data sets. So using this high spectral content, one can do quantification in terms of determining the abundance of the material. That means if you want to measure how much is the chlorophyll content in the leaf, that also is possible through making measurements about the absorption depth at red wavelengths or that red edge wavelengths, which basically typically people are able to quantify the chlorophyll content in the leaf itself. Then you can characterize also the variability in terms of how much amount of material is present in a pixel in terms of its fractions. Then you can also identify the kind of material which is present on the surface in terms of a typical mineral or in terms of a typical pigment, which basically gives a kind of a fingerprinting of the material through this hyperspectral data sets. Then you can also discriminate based on these characteristics, spectral signatures, about different type of properties, especially in case of vegetative systems, about different type of species variations can be discriminated using hyperspectral data. And then we can classify using some classification techniques these separate materials into the spectral similarity groups, in knowing that at what locations, spatial locations, what type of materials are present. And then of course detection. So detection, you can determine the presence of different materials in different objects and the processes which are leading to this type of detection. So all these type of remote sensing based identification, quantification, characterization, discrimination, classification activities are possible through this hyperspectral remote sensing data. Otherwise, using multispectral data, mostly it is all classification, but quantification and identification and discrimination at a finer scale may not be possible. On a broad scale, discrimination can still be done using multispectral data. Now, having told some basic fundamentals about these type of imaging systems, anyway, I'm sure that you will be given some practical demonstration. You have a drone there in your lab itself, and there are drone-based hyperspectral cameras are going to be flown. So you will get a practical exposure also. So different type of platforms are now currently being used for generating this hyperspectral information. So you have this ground-based systems, then you have the aerial systems, then UAV-based systems, and the space-borne systems are also in place when you can put the sensors on a satellite and then get a very regular information. There are advantages and disadvantages of all these platforms. Like if you are putting a hyperspectral sensor on a spacecraft, the advantage is your coverage increases significantly. You can cover large parts of the world in a repeated manner more frequently compared to what you can do through an aerial platform, where you have to have an aircraft, you will fly, and then you will collect a limited data over area, and then again you have to do a lot of efforts if you want to cover that area again, because especially in case of vegetative system, it's not only one-time observation. Observations throughout the cropping, stages is also very important. Then similarly, UAV also can give you very high resolution, but it will have a limited special coverage. So if you want to do only over a field or a group of fields, then UAV is helpful, but it will not be able to cover large part of the geographical regions. Let us say district or a state level acquisitions will be very difficult to cover from UAV. So each and every platform has its own pros and cons. So depending on your applications, you can choose the platform. So I am showing you some of the examples of this ground-based, hyperspectral data sets. Since many of you are specific to crops, so some of our colleagues have, developed over a period of time large amount of spectral libraries or the data sets over various crops, which basically can be very much useful in terms of, as I told you, crop discrimination, red edge dynamics, hyperspectral, spectral profile generation, and then relating it to, various biochemical properties like leaf nitrogen and then chlorophyll, etc., etc. So these are the primary objective of collecting this ground-based data set. So there are, I think you will be also exposed to some ground-based data collection using some ASD spectrometers, etc. in the lab where you are currently undertaking this training program. And so this is the typical, hyperspectral profiles you get for different type of, crops like rice bean, black gram, green gram, cowpea. You can see there are characteristics, differences in terms of the spectral signature for each of these crops. There are also differences in the healthy and the disease crop. So like especially in the IR region, for healthy crop, you will have more reflectivity compared to the disease crop because of the changes in the intercellular space itself. And then of course, in terms of water availability in the leaf also will play a very important role. So this type of spectra are produced on the ground, and similarly using space-borne system, this type of imaging spectra also can be produced, where you can see the agriculture areas are shown in the red color. So there is a satellite called Hyperion. It used to be there, now it's not functioning anymore. And using Hyperion satellite data, large amount of hyperspectral data has been collected. And this is how a typical spectral profile also looks like from Hyperion data, where you can see this particular signal of red edge, especially at around 670 nanometers or so. So using this type of spectral signature, now how to extract information. So there are different type of techniques called derivative analysis, discriminant analysis, principal component based analysis. Don't go into, don't worry about these too much technical terms. I think there will be specific lectures on data processing also. So using some of these techniques and simple hyperspectral indices also, one can generate information about healthy or diseased plants by taking certain combinations of wavelengths. Similarly, this is basically another slide which shows you about discrimination of various horticulture crops. So these are all spectral signatures of banana, cabbage, carrot, and tea. So you can see that banana has a very different spectral signature, especially in the IR region, compared to what you have for the broadleaf of tea. Banana leaves are very, very different, much, much broader. And compared to cabbage will have, more spectral dominance in the blue part also, compared to, the more the absorption, which is much more in the blue part from tea or let us say banana leaves. Similarly, there are characteristic differences in the IR part of the electromagnetic spectrum also for many of these horticulture crops. Similarly, this is a spectral signature for castor, groundnut, and red gram. Red gram has a very high, reflectivity in the green area because they will appear much, much darker compared to your groundnut, which has less, red reflectivity. And then the red edge signal is also very strong in case of castor compared to the groundnut and red gram. So based on these type of finer subtle spectral variations, one can also discriminate different type of crops on the ground. And then as far as the stress conditions, especially the water stress conditions are concerned, those also can be very nicely, captured. Let us say you have this, stresses which are there in the corn system, and then jowar, and then some other crops also. So you can see the spectral signatures itself will vary significantly for stressed crops compared to the healthy crops, especially in terms of their green reflectivity, in terms of their red edge signal, as well as in terms of the water content and the reflectivity in the IR region. This is another slide basically, which basically tells about the mangoes varietal discrimination. So this is two different varieties, Alfonso and Totapuri. Our colleagues basically in different parts, different seasons, they have also collected, the spectral signatures, and using some, discriminant analysis techniques, these varietal discriminations could also be achieved using the hyperspectral imaging data sets. Another very interesting applications now, apart from this crop applications of ground-based spectra, is also in terms of nowadays identifying, the genuineness of some of the paintings, because the kind of paints which were used by the original creators of the paintings will be very different compared to what you will have in terms of, somebody creating a copy of those paintings, because paintings nowadays sell very costly, especially those by the famous, artists. So people are using, this hyperspectral camera sets in terms of identifying, the characteristic pigmentations used by the original creators, and to, discriminate with a fraud copy of this type of painting. So there are a lot of literatures you will find in a lot of papers you will find in literature about these applications. So there are large amount of emerging applications which are currently being pursued by various researchers as far as the ground-based applications are concerned. So as I told you, in agriculture, for horticulture, crop varietal discrimination, crop stress discrimination. Then in case of document forgery, I told you, surveillance, security, food safety and control, especially food grading, the healthy food or a non-healthy food, fresh food versus old fruits. They also give information, specific information. Fruit quality inspection, mineral mapping is another key area where geologists, they use nowadays hyperspectral technology for identifying very specific minerals. And then archaeology and history also, a lot of information is being derived today using hyperspectral data. Similarly, medical diagnostics, also skin related issues, a lot of hyperspectral imaging sensors are being used to determine different type of pigmentations in the skin. And of course, in water systems, especially for identifying the water quality parameters like chlorophyll A, suspended sediments, color dissolved organic matters, all these 3-4 water quality parameters can be very easily amenable through hyperspectral remote sensing satellite systems. Now, another platform which is anyway the topic of your lecture.
Excuse me, sir. The slide is frozen actually.
Now, can you see that it is moving?
No, sir, actually. Can you please stop the presentation and restart it from the concurrent slide?
Yeah. Now you can see. I was talking about this slide, then I'm going to the next slide now. Yeah. So the another platform which is basically going to be the topic of the training is the airborne platform. So you can mount these sensors on a UAV as well as on an aircraft. And we have done a similar exercise few years back when a
a sensor, a hyperspectral sensor called Everest. It has been developed by Jet Propulsion Laboratory. It is known to India, and it was mounted on an aircraft, and it has collected large amount of hyperspectral data at different sites over India. So this Everest NG campaign was done along with ISRO and many other organizations in the country, including IRI. And this was a joint airborne campaign of first of its kind in India, where this Everest NG hyperspectral sensor was mounted on an aircraft which is owned by NRSC Hyderabad, and large amount of campaigns. This was that ISRO B-20 aircraft on which this Everest NG was mounted, and the sites were basically kept in mind, keeping different type of applications like natural ecosystems, water resources, snow and ice, geology and natural hazards, coastal and inland water bodies, coral reef systems, agricultural land and urban areas. So many kind of themes were chosen to collect data so that a comprehensive database of various natural ecosystems can be generated through this airborne campaign all over India. So two such campaigns were done, and today we have large amount of data, and I'm sure that Dr. Sahu may also be like to showcase some of this data to all the participants, because he may be having he was part of this particular campaign. So this is how this airborne data stack looks like. What you see, the red color is basically your typical false color composite, where the vegetation areas looks much red in color, and then soil exposed regions, water regions, etc. And on the third dimension, you have basically is the spectral information around these data cubes. Now, one more important thing which I need to tell you, that when you collect this data from an airborne or spaceborne satellite, it's typically known as the top of the atmospheric radiance data. It is the basic unit or the physical unit in which the data is collected is called radiance. So radiance is the unit of energy, basically, where you are getting the reflected energy. And then to convert this radiances into the surface reflectance, some amount of pre-processing is done. You have to basically normalize the radiance data with respect to the incoming solar flux, as well as in case of spaceborne data, do atmospheric correction. So there are specific software systems which basically helps you in removing the atmospheric component and then generate what we call as the surface reflectivity. So what you are seeing here basically is in this case for different locations like vegetation, water, and then minerals and bare soil, top of the atmospheric spectra in red color, as well as the bottom of the atmosphere. That means at the surface, once it is corrected for the incoming solar radiation and atmospheric effect, this spectra, like in blue color here, is the typical reflectance spectra of the surface. However, when you have the spectra from the air, it also will have the atmospheric component. As you can see here, the red color, the spectra for red spectra in same wavelength is much higher for vegetation compared to the blue, because it is also having now signal from the atmosphere by Rayleigh as well as by the mean scattering. That means the atmospheric molecules also are contributing. So you have to remove it and then generate the true surface spectra. This process is called atmospheric correction process. Similarly, now you can see for water also, the red line is the top of the atmospheric spectrum, and then the blue line is the bottom of the atmosphere or the corrected spectra. So there is a significant difference. So using top of the atmospheric radiance spectra, you cannot derive much information about the surface. You need to generate the surface reflectance curve. Then only you can derive the meaningful signatures. This is what we want to convey using this slide. Now, this type of pre-processing steps are basically where you need training and a large amount of experience in terms of handling various atmospheric correction or atmospheric scenarios and generating this surface reflectance spectra, because entire interpretation in terms of generating information will depend how accurately you have corrected this top of the atmospheric spectra and derive the diagnostic absorption features in the hyperspectral data sets. Now, as far as this Everest NG thing, as I was telling, it was mainly used for various applications like geology and soil, mineral and rock discrimination, and then agriculture ecosystems, especially in terms of species and community discrimination, density, cropping density, biophysical parameters like chlorophyll A, or the FAPR, fraction absorbed, photosynthetically available radiation, phenology, stress, disease. In terms of forest ecosystems, identifying forest areas which are basically vulnerable to forest fire, etc., etc. And the dry leaf accumulation also will lead to, providing fuel to the fire. So in general, in terms of agriculture, etc., the broad term which you hear is called precision farming, under which, a lot of issues related to crop insurance, carbon cycling and nutrient dynamics also today are very important. And some of these hyperspectral data sets can provide you a lot of information, especially about crop stress, pest and disease, and then soils wherever they are exposed, about the soil organic carbon, and then the nutrients which are available in the soil also can be discriminated up to a certain extent. So the data becomes very useful for this type of applications. In the water, as I told you, water quality is a very important parameter. So water quality parameter like chlorophyll, clarity of water, turbidity of water, all these things can also be quantified using this data. Urban scenario, you can classify the roof types, road types, whether it's a tar road or a concrete road, a pervious surface or an impervious surface. These type of discriminations are possible in the urban setting. Snow and glacier is very important because, especially in the North Indian rivers, by melting of snow and glaciers, they provide a lot of water for irrigation purpose. So we can discriminate snow type, we can estimate snow grain size, snowpack density, using this type of observation. Now, these are some of the examples where this average NG data has been used by colleagues in terms of crop discrimination for various crops as well as oil crops. So you can see these are the spectral signatures which has been derived using data for wheat, for coriander, for chickpea, for methi, many other crops you can discriminate here. And using some kind of classification techniques, especially there is a very famous classifier called, a SAM classifier, spectral angle mapper classifier. So such type of techniques are basically used to classify this hyperspectral data into different classes like coriander, lake. All these fields you are able to discriminate because the data was there at 4 meters. And which field is growing, which crop, we are able to successfully detect it. Type of data sets. Similarly, there are different minerals which has characteristic absorptions in the IR part of electromagnetic spectrum because of the presence of water. So like different clay minerals and the alternated minerals, they have very specific absorption at around 2300 nanometers to 2200 nanometers. Curves. Absorption.
ब्रेकफास्ट किया था ना उधर तो आपको कहना चाहिए था लंच करेंगे नहीं जैसे बनता नहीं है यहाँ पे बाहर पूरा चल रहा है कैंटीन में ये सामने वाली नंबर में हां ये कैफेटेरिया
there is another which is basically in terms of detecting the leakage or the gas leaks. So using this type of absorption lines of methane, 2300 nanometer, you can discriminate the methane seepage all across over certain areas. So methane seepage is normally happens over over the petroleum plants, and then there are natural seepage of methane. Also methane is getting released into atmosphere. So this type of greenhouse gases also can be detected using this hyperspectral technology. This is a very important example where the methane can be detected from airborne or from a UAV sensor, especially over areas like agriculture fields of water, rice, or maybe wetland systems. or even if, there are certain, plants over which the methane is getting emitted, these type of applications are also becoming very popular. Now, as far as the space-based systems are concerned, the satellites also carry a large amount of these hyperspectral sensors, and many such sensors have been flown
Sir, please unmute.
hyperspectral data cubes have been, have been collected using HISIS sensors also. So there are, different. I can go on and on. There is no limit for giving you various examples. But I am sure that through this training program, details of each of these, techniques and methods which I am telling will be told to you. However, there are a lot of scientific tools or data processing tools you will come across, and I don't want to frighten you by these names, but these techniques called MNF transform, pixel purity index, and member selection, spectral angle mappers. These are match filtering techniques. These are the different methods of processing the hyperspectral data through which basically you can generate a specific information about the kind of work which you are trying to do. Now, this is one example where using Prisma data, in Ladakh region, our colleagues could generate the specific signatures of different minerals, and then they could generate a lithological or the mineralogical map in Ladakh region using our Prisma data sets. This is another very interesting example of our HISIS data, where you can see that in the visible NIR region, we in FCC, we are not able to see, we are able to see vegetation and other things. But when we take a color composite of the IR bands, you can see that there are some very bright features in this area. So what are these bright features? So if you go and see the very high resolution data, these are all the solar panels. So nowadays, a lot of solar panels are also being, put for generating solar energy. And if you see the vegetation spectra and the solar panel spectra, there is a large difference in the IR spectrum of solar panel or the silicon spectra compared to the natural vegetation spectra. And using this type of spectral signatures, one can identify where are the solar forms are there, or how many solar forms are there in one area, how much energy is getting generated, even across borders, our, like on the eastern and western borders, what kind of infrastructure in terms of energy resources is present, we can identify using this type of spectral signature. So this is a very interesting example I showed you, where you can identify the silicon-based photovoltaic cells using hyperspectral technology. Now, coming to the end, we talked about various applications on Earth. But, now this technology is also being used to know more details about Moon and Mars and other planetary bodies. And India has, as you are aware, has launched 2 missions, Chandrayaan-1 and Chandrayaan-2, where these hyperspectral sensors were, flown. And many of you must have heard that India found water on Moon. So earlier it was thought that there is no water on Moon, but this type of a water map was produced simply because, the absorption due to these water molecules can be detected at around 3 micrometer range. So if you see this spectra at 3 micrometer range, there is a sudden dip, and this dip is caused because of the presence of water molecules. So this became the famous discovery that using a large amount of data, people could come out with a water map, especially the North Pole and South Pole region, blue regions, basically have shown abundance of water onto the moon surface using this type of spectral signatures. And later on, not only water, using hyperspectral data, the water ice could also be identified onto the moon surface. And then later on in Chandrayaan-2, we have flown another very interesting hyperspectral sensor, having a spectral range from 0.8 to 5 micrometer. And using this type of hyperspectral data sets, we could very clearly identify this absorption due to water. What you see here in the red spectra, there is a strong dip at around 3 micron or so. And this happens at locations which are basically having more water molecules onto the moon surface. The other spectra you see, they don't show this type of absorption curve. So using this type of spectral signatures now on moon surface, scientists are able to find out which are the locations where water is available onto the moon surface. And then, of course, in permanently shadowed areas of moon where the water ice is also present. Similarly, similar such work has also been done in case of Mars also, where large amount of minerals which are basically formed by clay formation or the the presence of water, they have also been identified, which tells about the aqueous history or the water history of the moons as well. This is another interesting slide from the moon itself, where the polar areas or the lunar poles, as you go from equator region to the polar region, you can see there is a large amount of presence of water in terms of absorption signals have been detected on the lunar polar regions also. So this technology is now not only limited to Earth-based applications, but it is also playing a very important role in providing a lot of discoveries about our celestial neighbors like Moon and Mars, and of course Jupiter, etc. also. So the technology is very wonderful. Only its application and its interpretation is very, very challenging, and that is where I think this particular training program will be very useful to all of you, so that all of you can learn how to analyze this data and how to generate meaningful interpretation of this data set. So I will end my lecture by showing you this particular very beautiful slide showing a part of the moon surface itself, where you can see very beautiful structures. So we don't know what these structures are made of. So hyperspectral data now our scientists are analyzing to try to understand what is the composition of these type of features which you find on moon. So not only moon, these many mysteries over the Earth surface also are nowadays getting resolved by the hyperspectral remote sensing. And I'm sure that this particular training program will be very useful to you in terms of understanding the theoretical aspects, as well as in terms of understanding the practical aspects of handling the hyperspectral data sets. Thank you very much. Now back to the organizers.
Yeah. Thank you so much. Such a wonderful exposure with respect to starting from the sensors, basic principles, and all possible applications from soil to plant to Mars and the moon. And it's not only the mystery in the moon, also mystery in the Earth's surface processes. What's under your mentorship, there are huge team working in country for the imaging spectroscope for different applications. And the wonderful lecture, I think it's very exciting. And these young minds will be looking forward to interact maybe in future, maybe on the chat box, there may be some questions. I'll get back to you if at all there is some questions from anybody who wants to work physically here. Any question you want to raise? One or two? You have anybody?
Can we ask?
Okay, please.
Sir, I have a question. What kind of sensors are used to capture the images of planet surface which is not Earth, like moon surface or Mars surface? Like, what kind of satellites and sensors are used in that domain?
Yeah, so actually the sensors are more or less same only. Here what we will use for Earth remote sensing, most of the sensors are basically what we know as the charge coupled device or CCD sensors. So, a very simple example of some of these CCD based sensors also you have in your mobile phones to have very high resolution. So similar type of thing, only the spectral range can be extended. Once you go to the IR part of the electromagnetic spectrum, your detectors will be different. So the same sensor is basically put onto these satellites also, which is normally flies on the Earth's surface. Only thing is the object basically looks very different to what we see when it compares to the Earth's surface, because like on Moon there is no vegetation, there is no air, there is no water. So the Moon surface is very different compared to what you see on the Earth's surface. Otherwise, sensor technology-wise, mostly the push broom and technology along with this CCD-based sensors are only being used.
Thank you, sir. Thank you.
So,
And I think
so
we
just
you can,
continuation to what sir said actually. So like for Earth, when we are observing Earth from a sensor of satellite which is launched in Earth orbit, so the distance of the satellite sensor to Earth surface is smaller than when we are actually trying to see Mars. So uh, like what kind of image?
Yeah, so it's not like that. See, Earth, typically, the low Earth orbiting satellites are operating from 500 to 600 or 700 kilometers, depending on the kind of orbit you have chosen. So that is the typical low Earth orbiting satellites. But in case of Moon or Mars, also the satellites operate around the surface of Mars. Like Mars orbiter mission, India's Mars orbiter mission was taken up to Mars, and then it was orbiting in the elliptical orbit of around 400 kilometers to 80,000 kilometers. Over Moon, our Chandrayaan-2 is orbiting only at 100 kilometers from the Moon surface. So it's not that we are seeing Moon from Earth surface or Earth orbit. We are taking the satellite closer to the Moon, and then it is put into the gravitational influence of the Moon, and then it goes on the Moon surface. Okay, so distances are, like in Moon, I told you only 100 kilometers, much lesser than an orbit typically for a Earth observation satellite here on Earth.
Thank you, sir. Thank you.
Thank
Thank you so much for again wonderful talk. And since morning you were engaged with us, though you had meeting with Chairman ISRO and many other engagement being in the chair of NRSC. So thank you. We'll get back to you soon, sir, again for further walk together.
Thank you. Bye.
Thank you. Bye. Thank you, sir. So I think we can stop now. Video. So we'll break for lunch. Lunch is arranged in the farmers' guest house. So we will be escorted by staff. And so it's now going to be 1:25 to 2:30. We will take up the next session. So it's 5 to 7 minutes walk to the guest house. We know many of you are staying there. So have the lunch there and come back. So by 2:30 we are going to start. By 2:25 we should be here. So you can leave everything here. You can leave everything here. So you don't need to carry. Other questions? Listen, by 2:25. Join by 2:25. सर अभी जैसे किस टाइम तक चलेगा सेशन? 5 बजे। 5 बजे तक। 1 2 3 3 आवर्स। Two 230, 225. We'll resume by 225. 235 नहीं, 225 they should resume. 230 class शुरू होगा. How slow ना? Yeah. प्रकाश चौहान को कर रहे हो आप, सबको करो. To all. Who is taking care of IT part here? Vishal is supposed to be. To everyone.
Everyone.
To everyone.
No.
To everyone.
Everyone.
हाँ. करो दोबारा. प्रकाश चौहान को नहीं. तू करो ना. यहाँ 2 में जाओ. हाँ.
इसको करके
सभी छोड़ दो. अब जाओ. कहाँ है? सिस्टम क्या है? ओके. अब जाओ. Everyone in the meeting.
is already
ये अरुण वहाँ 4 से लिख दो कि it will start at 2:30. नहीं यहाँ से लिखो. नहीं हो रही ना.
वो नहीं हो रहा है.
ये सब चीजें बड़ी गड़बड़ है. माउस पे इधर कर दो. अरे अच्छा ये यहाँ से फाइंड पार्टिसिपेंट लिखा है ना, छोड़ो उसको. क्लोज. नाउ ये सर को सीट डालो ना. हाँ. क्या ना जब क्लास चल रहा तभी लिख देना चाहिए था. 2:30 शुरू करें.
अरे हाँ
voice is not audible.
Excuse me, sir. Sir, you're not audible.
Organization kindly see the audio response.
Yes, check.
Sir, try once.
सर एक बार आप ऑडियंस से पूछ लीजिए.
Am I audible? Now it is audible.
Okay.
From beginning.
So shall I start from the beginning?
Yes, sir. Yes, sir. Yes, sir. Thank you, sir. Thank you.
Continue. Okay. Slide to move कर दो. Slide show कर दो. So data from the satellite is transmitted to the ground receiving station through a telemetry. Okay, once we get the data at the ground station, the data is maybe in any format. So the data should be there in the data. Maybe there may be many errors. Maybe there the errors may occur during the process of recording, transmission, scanning. So that data processing to be done at the in our lab. After processing of data, we get information from that data. When we arrange the data in systematic way, it becomes the information. Okay. So remote sensing systems include your source of energy, sensor, or I will say detector, target, ground receiving station, then processing system. That processing system may include the hardware and software. Then you get the results. Results in the form of tables, map, thematic maps. So this all include the remote sensing system. Any doubt up to now? Yes, medium is also included. So this is our yes. If this source of energy is sun, then that remote sensing is called as passive remote sensing. If the source of energy itself is available at this platform, then that remote sensing system is called as active remote sensing system. So depending upon the source of energy, we can classify remote sensing system into two categories: active remote sensing system, passive remote sensing system. The example of active remote sensing system, you see radar is an example of active remote sensing system. And we see the sun-synchronous satellites like and geosynchronous satellites, which depend upon the sunlight's energy. That those are the passive remote sensing systems. Okay, so these are the components of remote sensing system: source, target, sensor, analyzer, and I have already explained. Okay, so the basic signal is your electromagnetic radiation. So let us try to understand what is electromagnetic radiation. So electromagnetic radiation is when time varying electric field generates the time varying magnetic field also. So those fields are perpendicular to each other. Both together these produce the signal in the form of electromagnetic radiation. Okay, so that those have the characteristics of frequency, wavelength. These are all very basic, so need not to explain in detail. So these electromagnetic radiations, we have range of electromagnetic spectrum. The electromagnetic spectrum starting from the short wavelength to longer wavelength. In the shorter wavelength, we see gamma ray, X-ray, ultraviolet. Then towards the longer wavelength, visible, infrared, microwave, and radio. So these all type of electromagnetic radiation can act as a signal. Okay. So in visible, we take the 400 to 700 micrometer, nanometer, 0.4 to 0.7 micrometer. In infrared, mostly in short wave infrared, 2 micrometer to 14 micrometer. Then in microwave, 1 centimeter to 10 centimeter. Likewise, in radio frequencies, much longer wavelength is there. So this type of full spectrum can be used for as a signal in the remote sensing, depending upon the what kind of information you want to detect. Now we will talk about the basic spectral characteristics of both all three: energy source, transmittance, and common remote sensing system. Energy source, our energy source are Earth as well as Sun. Okay, in Earth emits the heat radiation. Sun emits the radiation in shorter wavelength region. So we know that temperature of Sun surface is about 6,000 Kelvin. According to Wien's displacement law, the peak energy occurs at the 0.5 micrometer. Okay, so it is around. That's why we see the sun is yellow in color. Below 0.3 micrometer, the energy is mostly absorbed by the ozone, so that we cannot use. And in case of Earth, the most of the peak wavelength region is around 30 degrees Celsius, 27. Okay. The peak wavelength will be 9.6 micrometer for the Earth surface. This is the spectral characteristics of energy source. Can we use all type of wavelength region for the remote sensing? No, because some of the energy in the certain wavelength regions are absorbed, very much absorbed by the atmospheric molecules. Wherever the transmission is more, those wavelength regions only we can use for the remote sensing. Wherever the transmission is more for the particular wavelength regions, those wavelength regions are called as atmospheric windows. Okay, here you can see on the y-axis it is transmission, on x-axis wavelength. So these are the wherever these regions are there invisible, this transmission is high, this can be used. In the infrared, this can be used. This cannot be used. This cannot be used. This cannot be used. So atmospheric window regions only we can use for the remote sensing measurement purpose. So based on that, this atmospheric window, these are the some defined in the common remote sensing system. The from 0.3 micrometer to 14 micrometer multispectral scanners are used. In photography, it is 0.4 to 0.9 micrometer. Human eye is sensitive to only 0.4 to 0.7. Thermal scanner 8 micrometer to 14 micrometer. And in the radar and passive microwave region, it is 1 millimeter to 1 meter. So we have already talked with respect to source of energy. The remote sensing system is classified active remote sensing and passive remote sensing. Based on the wavelength region, we can classify remote sensing, optical remote sensing, thermal remote sensing, microwave remote sensing. In optical remote sensing, the energy is mostly reflected energy. In case of thermal remote sensing, the emitted energy is sensed by the detector. And in case of microwave, both type of, if it is passive microwave, the emitted energy is detected by the sensor. If it is active microwave, then the backscatter energy is detected by the sensor. In thermal vision, the wavelength of emission is in the shorter wavelength region, but in case of microwave, it is longer wavelength. This is the typical spectral signature. In the remote sensing, if you want to distinguish any object, there should be a distinguished spectral signature. Okay. Your signature will be different, your signature will be different. In the same way, the spectral signature of a object should be different to distinguish the object through remote sensing. Okay. So what is the spectral signature? Spectral signature is the plot of spectral reflectance versus wavelength. So this is the typical spectral response or spectral signature of here three type of features here shown. One for the vegetation, this solid line. Okay. Solid the plus dotted line, that is for the soil, and this is the for water. For the water, after in the visible region, it is some reflectance is there. After that, all the energy is observed. So if you will see the data in near infrared or after the visible length, water body you will see as a darker, totally dark in the image, because all the energy after nothing is reflected, so it is not detected by the sensor. So if nothing is detected by the sensor, then no energy is falling, so the digital number will be 0. So that in the image basically towards 0 it is black and higher number will be brighter. Okay. So in the water in the water wavelength, after the visible wavelength, some only 5% reflectance is there. After that, it is totally absorbed. In case of vegetation, you see the many up and downs. Okay, so here you can see high peak is there. This is belongs to the green, and this dip are because of chlorophyll pigment absorption. So in the visible region 0.4 to 0.7, in the typical spectral signature, the absorption is dominated by the pigments. In case of near infrared, you can say 0.7 to 1.3. There is sharp increase in reflectance. So this sharp increase in reflectance is because of leaf structure. Whether your leaf structure is healthy, more intracellular spaces are there. Because of intracellular spaces, there will be a total internal reflection. The total internal reflection will lead to the higher reflective energy. So if your leaf is healthy, then there will be more reflectance in the NIR region. And this line belongs to there is a transition between visible to near infrared. So this line is called as red edge region. Okay. After that, some dip are there. These are the dip because of water absorption. These are the water absorption bands. 1.4, 1.9. These are the water absorption. These are the energy and the water available in the leaf. Because of that, this energy is absorbed by the water in this wavelength region. Okay. In case of soil, it is typically these are the dips also because of water absorption. Any doubt? So these are the spectral signatures for different kind of features. I say object of features. So here you can see This is typically in this water. There are two type of clear water, turbid water. This is typical vegetation. Then dry vegetation. This is dry vegetation, and this is for snow. So different kind of features, spectral signatures are there. Based on that, you can identify, distinguish the different objects. For each object, there is a variability in the signature. These are the typical median signatures. So always there will be statistical variation. Okay. So how if two features, spectral signatures are not statistically separated, then there is a chances of misclassification. One feature may get into another class. This feature may get into the another. So there will be a chance. So your classification accuracy will not be 100%. These are the some list. This is different wavelength regions is used for different purposes. So here I read out the wavelength region is using for mapping coastal water areas, differentiating soil and vegetation, mapping polar side and cultural features. In green wavelength region, it is used for the characterizing healthy vegetation and also cultural features. In red, it is used for discriminating different plant species, discriminating soils and geological features, and cultural features are near infrared region. It is used for the identifying vegetation cover, crop identification, soil, crop, land, water contrast. Also, we can features can be seen in the near infrared region. In mid infrared region, it can be used for the drought analysis, discriminating clouds, snow and ice, crop types, soil boundaries, soil and vegetation moisture content also. Now coming to the platform and sensors. So sensors can be placed, and to place the sensor we need some support. The support, the stage on which the camera or sensor is mounted, that is called as a platform. Okay. So based on the plate altitude, the platforms are classified into three categories: ground-based platform, or airborne platform, and space-based platform. In ground-based platforms, like we usually use the spectral radiometer. We go in the field, put on our back, and that gun will be there. Spectral gun is there. Then from that we take the spectral signatures. So that spectral radiometer, field spectral radiometer is used on the ground. That remote sensing also we say proximal remote sensing also. Okay. So spectroradiometer comes in our ground-based remote sensing platform. In our lab also, we bring the samples in hyperspectral lab. So that spectroradiometer used for the characterizing the samples. That is also in ground-based remote sensing. Okay. But we don't make any physical contact. That's what we say remote sensing. In the airborne remote sensing, drone, aircraft, the sensor can be placed on drone, aircraft, balloon. So if sensor is placed on that, then those type of remote sensing is called airborne remote sensing. And if sensor is placed on the satellite, then it is the spaceborne platform. Okay. In the spaceborne platforms, the satellite is placed in some orbits. Okay. So in case of, Earth rotates in westward directions, and our satellite orbits may make any angle from the plane of. So this is the, suppose this is the plane of Earth. Okay, so I am making the plane this Earth plane, and our satellite is making this angle. So this angle is inclination angle from the Earth plane. Which angle is making the satellite orbit? That is inclination angle. Based on the inclination angle, we can the orbits are classified in three categories: low inclination angles. If it is in the same direction as Earth moves westward, then the orbits is called as geostationary orbits. If it is in north-south direction, then it is polar orbits. And generally, these are the low inclination orbits are the sun-synchronous orbits. Sun-synchronous orbit means the orbits are designed in such a way that so when satellite see the ground, that match to the local illumination conditions, local sunlight conditions. For example, Landsat satellite or Sentinel-2 satellite, if pass through here, it comes 10 o'clock, 11 o'clock. So based on that, the orbit is designed in such a way.
इसको हटाना के लिए वो ऑडियंस के लिए जूम के लिए ठीक
This is the structure of sensor. In the structure of sensor, basically different components are there. I'll not go into detail of this structure of sensor. Basic, what I want to emphasize here, the angle which is subtend on the surface by the sensor is beta. So this and sensor is placed at the height at h height, then this in the 90-degree angle in the nadir. Okay, so this area covered by this sensor, it is called as a IFOV, instantaneous field of view. Okay, this instantaneous field of view means how much area is covered on the ground by a pixel. एक पिक्सल का कितना एरिया कवर हो रहा है वो आपका IFOV है, और टोटल एरिया whatever it is covered by a field of view in one scanning, that is called as swath. Okay, so this instantaneous field of view decide your resolution, spatial resolution. I'll talk about the spatial all type of resolutions. Pardon? Speak loudly. Field of view is whole view. I have to tell you that the sensor is made up of some type of suppose CCD camera is there. Okay, so in CCD camera for each different it is made up of many small sensors. So one sensor belongs to the one ground cell, one IFOV. So all sensors suppose in CCD 1000 small sensors are there, all 1000 IFOV मिलके एक FOV बनाएंगे, तो how much area is covered? Yes. So how much area it is looking by all the sensors, small sensors in the on the detector. Okay. Let me explain again. Suppose this is the different sensors are there. Each one is different. So this is covering this much area on the ground. Okay. So this is the 1 pixel is covered. Again, this pixel is covered by this sensor detector. Then this is again then this is, so how much area is covered by this? This is the field of view, and this small is this is IFOV, right? Now coming to the resolutions. How you will know the your quality of the data collected by the sensor? So resolution will tell you what is the quality of your data. Okay. So sensors specification is determined by 4 type of resolutions: spatial resolution, spectral resolution, radiometric resolution, temporal resolution. Okay. Coming to the spatial resolution. Spatial resolution is the capability of sensor which can detect the smallest, which can distinguish the smallest element or object on the surface. Suppose the spatial resolution of a sensor is 1 meter. My 2 hands are apart 1 meter. Okay. So that sensor can distinguish these both hands. Now my hands are within the 1 meter. Now the sensor will tell this is the one object. Okay. So your spatial resolution will tell the smallest distinguishable element. How much is capable the sensor? Okay. I'll say that coarse resolution means the spatial, the grid size or pixel size is more. Here. Any problem? Okay. इधर ठीक है. I'll say spatial resolution, coarse resolution, fine resolution. The pixel size 1 by 1 kilometer is coarse resolution, then 1 meter by 1 meter. So I'll say 1 by 1 meter is finer resolution, and 1 kilometer by 1 kilometer is coarse resolution. Okay. Spatial resolution depends upon the resolving power of the sensor, and resolving power of the sensors depend upon the which lens is using, what is the focal length and all. Okay. So even though resolving power of a sensor is much finer, then even though resolving power of this sensor is much finer, but spatial resolution may be coarser, because it depends upon the other components also. Other components means what is the medium also. If haziness is there in the atmosphere, that also determine the your spatial resolution. Okay. So any doubt in the spatial resolution? Now coming to the spectral resolutions. Spectral resolutions is the capability of the sensors which can distinguish the smallest spectral wavelength region. The observation in which we made the spectral wavelength regions are called as spectral bands. Okay. So suppose we want to get this signal in the red wavelength region. In red wavelength region, I am saying region, then it must start with start with the starting wavelength, then ending wavelength. So any sensor's spectral wavelength is characterized by the central wavelength lambda c, and the wavelength width is determined by the lambda 1, lambda 2. If I subtract lambda 2 minus lambda 1, that is delta lambda, here is wavelength band. If I want to measure the light, the energy in red wavelength region, then the filter must pass through the only red light only. It must block the all the other wavelength, cut off the. So a practical filter on the y-axis I am saying intensity of electromagnetic radiation, and on x-axis is wavelength region. Okay. Suppose for the red wavelength region, the wavelength region is start 610 to 690. Okay. So ideal filter. How this is intensity 0, it is 1. Okay. So ideal filter, how it will be, this will be like this. It will block all the energy below 610 and above 690. But in practice, we doesn't get the ideal filter. What we get? We get filter like which makes the some Gaussian type of curve. Some energy below 610 also will also reach to the detector also, and it will sense by the detector also. Some energy above the 690 also will be detected by the. So spectral resolution is characterized by the specified by the where is the half maximum 50%, 0.5. So and this will be the your lambda 1, lambda 2. So spectral resolution is defined in terms of this region, and this region is called as full width of maxima, FWHM. Okay, full width of maxima. Whenever you will see any sensor specification in case of satellite or drone sensors, you can see in that what is the FWHM of a spectral resolution. Okay. Based on different wavelength interval, the already I think in previous speaker already explained the multispectral and hyperspectral, so I am not going into detail. Coming to the radiometric resolution. Radiometric resolution is the capability of the sensor, how much smallest change in the energy level can be detected by the sensor. Energy level means, suppose energy level I am measuring in the watt per meter square. Okay, so it is sensitivity is 0.1 watt per meter square, or 0.01 watt per meter square, or 0.001 watt per meter square. So how much sensitive to the smallest change in the incoming energy, that tells the radiometric resolution. The energy detected by the sensors is quantized in different levels depending upon the bit system. So your radiometric resolution is represented in terms of bit levels, whether it is 8-bit system, 10-bit system. Suppose 1 watt per meter square energy is coming, and that energy is quantized into 8-bit system, then the energy levels will be and the value will be 0 to 255. Okay. So that tells your radiometric resolution. Okay. So the quality of signals will be determined by the radiometric resolution. Fourth resolution is temporal resolution. Temporal resolution is the same area, how frequently at the same time we are scanning again. So this tells the repeatability of the sensor system. In drone, anytime we can take, so it doesn't apply to the drone systems, so it is mostly for the satellite systems. Okay, up to now, any doubt, any clarification, any query? Yeah, sure. "20 nanometer is your bandwidth. You have to specify 20 nanometer bandwidth with the central wavelength of 610 nanometer. So your wavelength region will be 610 minus 20 means 590 plus 630 to up to 630. Yeah. Yeah. It depends upon the water in which form is available. It is whether it is wound water or free water. If it is wound water, the absorption will be more. Free water is there, then attenuation will be less. So here you can see, in case of spatial resolution, here much more clear distinguishable in the high spatial resolution image compared to the other spatial resolution image. In case of spectral resolution, it is already explained, more number of spectral bands are there, shorter wavelength interval will be less in case of hyperspectral. In case of multispectral, it will be more. Okay. So this is the triangle of spatial, spectral, and temporal resolution. The higher the spatial resolution, you will get the more finer details. If it is low spatial, the detail will be coarse. In case of spectral resolution, higher spectral resolution will be, there will be many bands with shorter wavelength interval, that is hyperspectral. If it is few bands with the
स्लाइड फ्रीज हो गया पर रिवाइज करके मैं अगेन
हो गया तो यहीं से करोगे। In case of temporal resolution, so we are agriculturists, so agriculture is grown over a season, so we have to take many images over the years. That also form the basis for classification or identifications of the features, okay, and characterization of the feature. So temporal resolution is also important in case of suppose you want to study the phenology of the crop, then you have to take the multi-grade image. These are some examples of hyperspectral sensors for ground-based, airborne, and satellite-based platform. In the ground-based platform, spectrodiometer, FTIR, Fourier transform, infrared imaging spectrodiometer, spectrometer. In airborne, there are many sensors are there: HiMAP, probe, CASI, Averis. In case of satellite-based, EO, Earth Observation 1, Hyperion, IC. Now coming to the some overview of digital image processing. Once we get the data, what we will do with that data? We want to deduce some information with that data. Then we have to do digital image processing. Okay. So digital image processing is a subject deals with the numerical transformation of the images to produce desired image. Why I am saying it is numerical transformation? Because the data is coming in terms of numbers, digital numbers. So any numerical transformation we will do, that is digital image processing. In case of remote sensing, digital processing would mean deriving information from remotely sensed data using a computer. So central idea of digital image processing is the data. It is Landsat image. These are the numbers, the fed into the computer, and we get the some results output in terms of either table, thematic maps, and anything. So this is the, so first we will try to understand what is digital number. Okay. Digital number is a two-dimensional discrete signal. Two-dimensional discrete signal. It is not continuous. If it is continuous, that signal will be analog. Two-dimensional discrete signal which is captured by the or sensed by the signal and stored as a number in the form of row and column. And the smallest element of that scene or feature is called as a pixel. Pixel means picture element. The value of picture element pixel is called as digital number, right? So what digital number tells? How much energy or light is striking or falling on the sensor and converted into a number, that is digital number. So digital number will tell the brightness level of the scene or image, right? The total number of pixel in an image can be calculated through the number of rows and number of column and which uh, radiometric resolutions we are using, bits per pixels. Okay, so number of colors or gray levels will be 2 to the power bits per pixels. So size of the image also we can calculate, row multiplied by column bits per pixel. Suppose our image is 100 by 100 pixels and we are using the 8-bit system. So bits per pixel is 8. Then the 80,000 bits will be there, and so the size of the image will be 10,000 bytes and 10 kilo, less than 10 kilobytes, because it will be divided by 1024. Remote sensing data typically stored in the 3 formats. Whatever the remote sensing data, typically, there may be other formats are there. Band sequential, because remote sensing data, multispectral data is there, in different spectral bands are there. So band sequential, BSQ, band interleaved by line, BIL, band interleaved by pixels, BIP. In band sequential, suppose 4 bands are there, 1, 2, 3, 4. So in the file, you just imagine a text file. In the text file, all the data of one band is written continuously. Then it is followed by the second band, then third band, and then fourth band. Now we know that the formatted band sequential. Now I'll this file I'll open with some software. I'll give the information that this format is BSQ. So software automatically read in that way and give you in the image format. Okay. In case of band interleaved by line, for all the bands, the first line will be written, then second line up to n line will be written, then second band, second row will be written, third row will be written. So the data is written line by line. So that is what it is called as band interleaved by line. Okay. In case of pixel, it is for all the band, first pixels will be written, then second pixel will be written for all the bands. So it is written pixel by pixel basis. Okay. So in 3 formats, the remote sensing data is stored: BSQ, BIL, BIP. You have to know in which format this data is stored. Then only the software, otherwise software, now software become intelligent, so they know in which format it is written. Some header information also written in that image file. So our software automatically open that file that it is in the BIL format. Yeah. Ji? All are standard form. Mostly it depends upon the data recording process. The data comes in different format that is processed at the ground, and in which format it is written, that is depend upon the user. So what generally what we see in Landsat, Sentinel, the data is provided in band sequential format. But many data is provided in BIN and BIP format also. Mostly BSQ format is followed. Why we need digital image processing? As I said, the error may occur during the process of recording, when data is recorded, or scanning, scanning, or data is transmitted from satellite to ground station through telemetry. In that process also, the error may occur. The error may occur, the degradation in data may occur because of atmosphere also. Okay, so those errors has to be minimized or eliminated. For that purpose, we need the digital image processing. So I enlisted 5 basic purpose of the digital image processing. First is image rectification and restoration. If the data error occurred because of any reason, for that purpose we have to rectify the image. Suppose our images look like this, but original image is coming like this. So we have to rectify this. Some shiftings we have to do. So we have to do the geometric corrections. So the geometric correction, sorry, दोबारा क्यों? Okay. Geometric corrections and radiometric corrections are the part of image rectification and restoration. Second purpose is image enhancement. You want to interpret the image visually. आंखों से देख के आपको some information you want to get. For that purpose, we need enhancement, image enhancement. So for deducing the information visually, we need some image enhancement. There are many algorithms which is used for the image enhancement, like gray level thresholding, histogram equalization, so density slicing. These are the procedure of image enhancement. Third is image classification. You want to an area to classify automatically. You want to classify the area in different land cover type, and you need the, you will not go everywhere. This is the one crop, this is the forest, each pixel. Then so you need some automatic algorithm which can classify your image into different land cover type. For those purpose, we need the digital image processing. So there are algorithms for the image classifications: supervised classification algorithm, unsupervised classification algorithms. Fourth purpose is data merging and GIS integration. with the image you want to analyze some other attribute data. Suppose land cover type data is there and population density data is there. For both analysis you want to do altogether, then you need the data merging and GIS integration. Fifth is biophysical modeling. Remote sensing gives the only numbers. Okay, so I want to get the crop yield. How spectral information is converted or translated into the crop yield data. For that purpose we need the biophysical modeling. This is all about my presentation. If you have any doubt, you can ask me. We are talking remote sensing data is always raster data format. GIS format data, other is line, point, polygon will be vector data format. कोई link नहीं. These are the remote sensing data formats are raster data formats, and raster data formats can be stored in the BIL, BIP, BSQ format. The vector data format cannot be stored in that.
No question? Any question from the chat box? Any question? No question. So let's give a big hand to
Thank you so much.
So
Thank you, sir. Thank you.
on behalf of
Thank you, sir.
Thank you. Thank you.
I hope you liked my presentation.
So he is available here. Anything, any clarification you want?
Even after of this session or any time you can ask me any query related to an arrangement also.
Yeah, anything.
Anything.
So we can break for tea. It's now 3:45. We can resume at 3:50. Sorry, 3:55 or 4 o'clock. Okay. So we can break tea there outside. We'll resume at 4 o'clock.
Sir, can you unmute, please?
Not audible, sir.
Intelligence, further machine learning and deep learning technology against very large, diverse big data sets that include structured, semi-structured, and unstructured data from different sources and in different sizes. When I say structured, semi-structured, and unstructured data, what exactly it means? So structured data, what it is having a high degree of organization. That means if we are taking Excel files, we can consider it under the category of structured data because every column in your Excel sheet is a representative of a header and it is having some column information. For example, when we are talking about some files in agricultural aspect, so those columns or the Excel sheet might contain the ground data that you are required, such as some soil parameters which belong to nitrogen, chlorophyll, sorry, nitrogen, phosphorus, potassium. So all those parameters can be listed down. And also the other columns can consist the reflectance data if I'm talking about hyperspectral. So if you'll be seeing the demonstration of spectroradiometer. So that in spectroradiometer, we are having the range from 350 nanometers to 2500 nanometers. So every column would be a representation of reflectance value per nanometer. So here, structured data can be referred to that, which is highly organized in form. When I'm talking about semi-structured data, it is having comparatively lower degree of organization, in which I mean to say, for example, the header files which you are downloading with the satellite data, it might be having some information when the data was acquired, what is the format of the data that you are working with, what are the spectral range in which the data was acquired, the number of bands, and some other things also. Further, Dr. Rajkumar sir mentioned about the FWHM, some sort of information, or all those things can be included in the header file. So we can consider it as a semi-structured data set. Further, we come on to the unstructured data. For example, if I am gathering some JPEG files, some video files in order to carry out my research, that comes under unstructured data. It is not coming under any classification mechanism. If I want to detect a diseased leaf, so I'll be collecting the data which is having the leaf images, yeah. So that RGB data, which we are collecting from the internet, comes under the unstructured category. And also, I'm referring from different sources. We further in the previous slide we studied about the level of organizations in which we are capturing the data. So it can be from any source. It can be from the field, from the spectroradiometer. If we are using some sensors for some of the field, we can capture that data from ground. Moving on to the airborne, we are having airplanes on which the sensors can be mounted. If we are aware about the Everest NG mission that was carried out with ISRO and NASA and in collaboration with DRDO, which was having 425 bands, that is the number of bands that were considered, and the spatial resolution was between 4 meter to 8 meters. So it was carried out in 2 phases in 2016 and 2018. So you may see on the website also, the designated website about the Everest NG mission. So that is an example of the Airborne platform on which Everest NG sensor was mounted, and it collected the information over more than 59 sites in India. And and again, drones are again another example of airborne media. Further, spaceborne, we looked into the previous slide, and satellites can be source of this. So in different sizes, obviously. So if your region of interest, it depends upon your region of interest. If we are doing some agricultural studies, we'll be only interested in the agricultural land. Further, we'll be masking out the other details. So this is the brief or the genesis of big data analytics. Further, big data can be defined as data set whose size or type is beyond the ability of traditional relational databases. The data that we are processing nowadays is it is consuming a lot of space in our systems. Therefore, we are in a process to shift the entire system for analysis into cloud now. So we are in that transition phase. So, and also to capture, manage, and process the data with low latency. So in this image below, we can see that big data is not only about the volume of data as the name suggests, but there are other things which are associated with it, such as storage, where to store the data, and also if the data is stored, how we can analyze it, the visualization, and how we can take the benefit of cloud technology to again readily access our data and do some changes. So obviously, if you are aware about big data, we are knowing about the 3 major V's of big data, that is volume, variety, and velocity. There is the flowchart that we can see that here on the left hand side, in which big data is about the volume of the data, that is size of the data, velocity, the speed at which data is generated. If we take example of some social media platforms such as Twitter is there, Instagram is there, Facebook. So see the amount of data which is generated every seconds, and not in the form of text that we are commenting, in the form of videos, in the form of audio files. There is whole set of data which is available for you to process, to analyze. And if we talk in terms of airborne hyperspectral remote sensing, we are taking the data now in every alternate day in order to monitor the plants. So by volume of data, I mean to say that how big is the data and how big storage capability we require for this. Velocity, that is again the speed. On a single video, we are having a lot of comments, a lot of other audio messages are there. So variety, that is different type of data which I have already discussed. Veracity, so it's not that always the data is coming from a proper source. The data validity is also an important aspect. For further, the useful data, so it depends upon us which information we want to use and which we don't want to use. So validity, the data should be from valid source. Again, variability, it should be having for example, we are taking the data should be variable or dynamic enough, not only to extract certain features or to predict for the future also. Then the data is always distributed. Vocabulary considers upon the data models that we are using for analysis. We'll be discussing briefly about the data models we are using here. And vagueness, that is confusion over meaning of big data and tools used. That means there are a lot of algorithms mentioned in the literature. So which algorithm to use, which is the most accurate one to go for the analysis? These are some of the benefits which are listed, benefits of big data analytics which are listed. That is faster decision making. For example, in India, startup culture is growing nowadays. So we understand the value of data. And also, since if we want to gain some experience, we need to analyze the historic data in order to make any of our application or research a successful story. Then cost reduction and operational efficiency. If we are taking the data in one season through drones using airborne hyperspectral remote sensing, for the next season we make sure that the cost of going into the field and all these things are taken into account and these are reduced. So we try to take the historic data or the previous season data to predict the other parameters for the next season. So this is one of the example that we are using for this big data analytics. And improved data driven go to market. That means analyzing data from sensors. We have a lot of sensors which are there in our field to examine, say, our soil moisture is one of them. Devices are there. We are taking videos from drones readily from RGB sensors and logs, transactional application, and other things also in order to make use best efficient use of big data. This is the most common diagram that you will be flowchart you'll be finding for big data analytics. Later, I'll be linking the same life cycle with hyperspectral data also. So therefore, I'm not going into detail. So the first stage is business case evaluation. In this, taking again an example of agricultural application. If I want to maybe if I want to analyze or estimate nitrogen in soil or crops, what we can do is we can identify the problem. We can see the budget prerequisites further, whether the problem is actually belonging to big data, because nowadays we all are running after these tag words such as machine learning, deep learning, but we need to understand that whether our problem is exactly belonging to this category or not. Need not to go for deep learning if at all we see that the problem is readily solved by machine learning. It depends upon the number of observations that we are having. So, and also the computational part of your system. So there are multiple other aspects also in order to go for that. Then data identification. As researchers, we are having a lot of sources of data, incoming source of data, such as research papers are there. We are taking help of research papers. We are taking help of ebooks. Other than that, we are doing some surveys, or we are looking into blogs or attending workshops. So there are multiple sources of data that from which the data you can gather. And again, data acquisition and filtering. So all the data you need not to see into account. And data extraction. So the word extraction involves transformation. So in transformation, what exactly is, for example, I want to categorize you all on the basis of your height. So why data extraction is important or transformation would be involved. For example, I knew the minimum height, the maximum height of the participants, the average height. So here mathematical computation is involved. So therefore data extraction normally involves the transformation into account. Then data validation and cleansing, that is removal of any invalid data. You might have not any n values, not a number values due to because of your sensor, because of other illumination characteristics, atmospheric hindrances. You need not to use that data. We discussed about the atmospheric windows and all those things we discussed. So the data which is not in the acceptable form can be easily be removed by filtration or something like that. Data aggregation and representation. It is not advisable to work with multiple data sets for obvious reasons. So therefore, we can combine them together. For example, in GIS related problems, what we do is we combine the latitude, longitude details with the attribute details or the temporal details, so that we get that complete entity information. Then data analysis and data visualization is an iterative process. Till I am not satisfied with my data, or the accuracy of the model, I'll keep on iterating it with data analysis and utilization of analyzed results. We can further use whatever we have done the analysis or prediction or classification problem, whatever your field is, so that we can uh, further formulate the results for. Now adding this word geospatial in front of big data, what exactly it means. So geospatial, I guess we all are aware about, like geospatial data typically combines location information, attribute information, and the temporal information. For example, Google Maps is an example of GIS. So what we can see is if we are finding certain locations, so latitude longitudes are associated with that location. Further, the attribute information, for example, I want to know the nearby restaurants, the nearby petrol pumps, the attribute information about the names and other features can be mentioned there, and also the temporal information, how well it the for traffic routes we follow it, so the temporal information. And also geospatial data is information recorded in conjunction with geographic indicator of some time. We talked about raster and vector data already in the previous session, so no, I'm not going into detail. Then geospatial analytics is used to add timing and location to traditional type of data. For example, we are all aware about the COVID dashboards which were prepared by Ministry of Health and family welfare. So in that dashboard, we can click on the location. We'll be getting the latitude information, the longitude information, the number of active cases, the number of patients who have already recovered, and unfortunately who lost their lives. So the deaths also can be readily seen by it, and the cities which were having the most number of COVID cases. So it's an example of geospatial analytics dashboards were also seen at the time of COVID, and there are multiple other dashboards to see the temperature forecast. So all those things which are actually available on the IMD website also. So geospatial technology refers to the technology required for collecting, storing, and organizing of geographic information. So geospatial data collection and management, from wherever we collect the data quality is an important aspect. So we need to consider data quality, whether it is free from all of the errors which sir was also talking about, and also the solution is scalable, cloud based, to able to accommodate different file formats by using curated database. That is, we are collecting the data from different sources and optimizing the information. So this is the foundation of AI for geospatial big data. So considering or concentrating on only the stage 7, that is data analysis, we can see here AI or the artificial intelligence being the bigger circle, which is having the tendency to predict or to mimic the capability of a brain. And machine learning being the subset of AI, it works on the handcrafted features, and it also helps to learn from our previous knowledge and predict accordingly. Further, deep learning is again a subset which in this complete process is automated. That means, for example, in machine learning, what we do is we extract the features, but the features are automatically extracted and the things are predicted using deep learning. So it focuses on teaching computers how to learn without the need to be programmed for specific tasks. And the key idea behind machine learning is to create the algorithms. Machine learning is having three major components. The first one being the data set. If we are belonging to the agricultural fields, the data sets can be different. So if there are certain parameters that you want to predict, or you want to classify the diseased leaves with the healthy ones, that can be a data set that you can create. And further, the extraction of features. So every time there are a lot of features which are associated with your data set, that I talked about data extraction before. So that data transformation or feature extraction techniques can be looked into account. For example, if we are aware about a principal component analysis, that is PCA is the most standard one that we can use to reduce the dimensionality of hyperspectral data. I'll show you afterwards also. And the algorithm, obviously. So algorithm depends upon your application. You want to perform a target detection problem. For example, in agricultural field, if I want to count the number of tassels in maize field, it is a problem of object identification. Further, if I talk about classification, I want to classify different types of soil or different types of crops, is an example of classification problem. And for regression, there are a lot of macro and micronutrients associated with soil as well as crops. So that comes into the regression category. Moving on to the machine learning, just to give you the brief idea, we'll be discussing this in detail throughout the program also. So machine learning that is supervised, there is a training set with labeled data. Most of the times we are having the labeled data. We know the categories or the classes, and therefore we are involved in training the machine. So this data needs to be divided into three categories, that is training, validation, and testing. Why this categorization is important is to test the efficiency of your model. So therefore, depending upon the literature, you can go for different ratios. For example, 70, 15, 15 for testing, sorry, for training, validation, and testing. So it depends upon your application and the number of observations also. So when you are doing this sampling, you can randomly select the training data set followed by the testing data set, or there are multiple other strategies such as stratified sampling you can perform. So all those things can be included. So therefore, once the model is trained over the labeled data, you can give your model the testing data and check the testing accuracy. Further, you give the data which is not labeled in order to see whether your model is performing well or not. And also this types of learning is referred to as classification and regression. For example, you are performing a category wise task, already classes are defined, so that would come under classification. So if the output is discrete in form, so that is type of classification output. And in regression, the continuous output is there. For example, if I want to predict the temperature, so it would be a continuous one, not the discrete values or not the classes. So then comes unsupervised, in which on at the last, so in which unsupervised learning means we don't have any support of labeled data, and it allows the program to search for the patterns. So it would be searching the similar patterns on which it would be categorizing or clustering them down based upon the similar properties or characteristics. Then semi-supervised, as the name suggests, is the mixture of both supervised and unsupervised learning. So for example, in satellite imagery, most of the times we are not having the complete information or the complete ground truth that we might consider under semi-supervised category, because we are having information about small areas or our region of interest. So there is some area which is belonging to our interest, and we are having the ground truth associated with it. And further, as we see in the complete area, we might not have that sort of ground truth. So then reinforcement learning is very similar to how humans learn by trial and error method. So if we learn something good, we are awarded, and if we are doing some mistake, again some penalty is imposed. So therefore reinforcement learning comes into account. So again, deep learning, there is a difference between machine learning and deep learning. We can see the input, and there are two stages of feature extraction and classification. After that, the output is predicted. But when we are actually increasing the number of hidden layers, or we are adding the complexity to our models, then we result, or we come down to deep learning. So feature extraction plus classification gives me deep learning. And also there are some examples of other than agriculture, but that we can see in this. So the first one is image recognition. Again, I mentioned you about the data set. We can categorize the diseased leaves out of healthy ones. So image recognition is mentioned. Natural language processing, for example, the autocorrect option when we are dealing with text options. So autocorrect, auto predict options, so that comes under natural language processing. Then portfolio management or prediction of any of the agricultural aspect also comes under this. And in medical fields also we are using this. Speech recognition, what such as example of Siri. So it's an example of speech recognition. It takes our voice commands and process it and gives the output related to it. Further, robots and self-driving cars we all are aware of. So deep learning is a class of machine learning algorithms inspired by the structure of human brain again. So the basic functional unit of a human brain is known as neuron, similar to here in machine learning and deep learning. So it reacts in brain, we react towards the stimuli, and we try to generate the output. Where, for example, our eyes are behaving like a sensor. It is passing the information to my brain, and further it is being processed. So very similar in the machine learning aspect also. So whatever the sensor are, not the eye as sensor, whatever the other sensors are seeing or perceiving, that information is uh, analyzed using this. So therefore, that clears the importance of digital image processing that we were discussing in the previous session. So what all that the sensor has acquired is further processed. So there are certain challenges in big data. There is a sheer volume of data, we already know. Considerable storage is required. And also the data is in different file formats, like we were discussing about BSQ, BIL, and TIFF, and other formats that we want to process. Difficult to find the files that contain the data needed. So always it's not necessary that you'll be finding your area of interest in the single scan line. You need to mosaic further different scan lines. And it again happens in drones. It's the same thing. Geospatial data is stored in many different formats. Combining data requires data scrubbing and reformatting. Raw geospatial data requires specialized knowledge. So we need to understand all those parameters. So again, these benefits of geospatial data, that if we are working with agricultural field, we can issue advance warnings to the farmers in order to do the site-specific nutrient management or things like that. And if there is some disease attack to be, because if some small part of crop is damaged by some disease, it can be further looked into. Deeper understanding of this using geospatial data can provide organization with evidence by how some analytic solution can work well for our field, and for some other field it might not work. Then again, heightened efficiency. So in order to improve the efficiency of our model, we need to update or automate also. So geospatial data future. Now we will be discussing about the drones, which are actually now equipped with imaging, which from starting from the RGB sensors till the hyperspectral sensors or LiDAR. So it provides a treasure of information that needs to be processed, and also without going into the field. After some point, we'll be able to train our model so well so that it is predicting with a good accuracy. So this is for these are the big data analysis for sustainable agriculture. Why and where we can use it? So feeding the growing population, obviously. So farmers can rely on rainfall patterns, water cycle, fertilizer requirement, and there are multiple smart decisions that needs to be made. So such as recommendation systems can be there, active recommendation systems can be there, so that the farmer knows that what amount of fertilizers or some other things needs to be supplied to the crop timely, using pesticides ethically. So optimizing the farm equipment, if we are talking about smart farms, there are a lot of equipments that we can work upon. So giving these platforms that kind of capability can help us to increase the yield. Managing supply chains issue can also be helpful in sustainable agriculture. So now we have already understood this big data part. Now coming down to hyperspectral remote sensing. So hyperspectral data encapsulates rich spectral and spatial information. When I'm talking about the spatial information, it talks about the arrangement of pixels in a form of grid or band by band. And when I'm talking about the spectral aspect, I talk about the number of bands which are giving me that unique information. So also, therefore, a pixel corresponds to a high resolution spectral signature that uniquely identifies a target material. For example, for me, a fingerprint can uniquely identify me. So similarly, a hyperspectral or this spectral signature is a fingerprint which can uniquely identify an object. So there are different characteristics of different materials such as soil, vegetation, or different crops or minerals. So which are readily or by which we can actually identify that object. So remote sensing deals with the acquisition, processing, and interpreting of images, which we have already discussed. And also we have discussed about the source of radiation, active and passive sensors, atmospheric interactions, reflectance, transmission, and absorbance, interactions with the Earth's surfaces, and the sensor. So big data analytics is use of advanced analytic techniques against very large diverse. So we have already discussed this application. We can see the scale of change here from ground based, by which we can use the spectroradiometer to acquire the data. Further going to airborne. In airborne we can, again I've mentioned that we can use this the aircraft or the drones, and we can collect the data. Further the spaceborne is there. So spaceborne or multispectral imaging, further airborne hyperspectral imaging can be done, and further the corresponding data can be acquired from the handheld spectroradiometer. And again, on the right side of the window, you can see that how well we are able to identify each of the category or the end members which are considered here. So a mineral would be having a very distinguished spectral signature, water and vegetation. So by these characteristics, we'll be able to identify the classes involved. And not only this, we can go more dig deep into this by taking the abundance into account. So since vegetation is not only made up of a single component, there can be other components also. So therefore that can also be distinguished. The abundance values can also be taken into account. So again, how hyperspectral remote sensing can be considered as a big data problem. So we have already seen this flowchart in our first slide. So volume, that means the size of data. That means you can see here, this is a single day file. After processing it, we are getting a size of 36 GB. This is a single iteration of drone with hyperspectral camera integrated on it. Single collection, or this is the detail about these 62 files. That means different scan lines we are getting. So this is how big the data we have to process. So it need not, the issue might not be fixed with the local system. We need to shift to the other technology in order to readily explore it. Then velocity, the speed at which the data is generated. I said that every alternate day I am collecting the team is collecting the data. So therefore the speed at which the data is generated, and not only the data is generated with respect to the hyperspectral aspect. It is, we are taking thermal data, we are taking RGB data, we are taking multispectral data. So this is the frequency that how we are going. Variety, again different types of data. This here you can see the hyperspectral image. Here you can see the spectroradiometer. So the variety of data. Here again the field information about the macro and micronutrients. Then veracity, data accuracy should be there. So when drone is interacting with the surface or the surface properties of vegetation or soil or any other property, the data which is actually useful for you should be used. The outliers should be avoided. So sometimes because of the sensor, there are some outliers or there are some errors while noting down the data or acquiring the data. So that data should be avoided. Then validity, again, there are a lot of freely available spectral libraries available, and some commercial libraries also available. So which data you need to use as a reference is also an important aspect. Again, variability, that is evolving behavior of data source. If I'm considering again agricultural aspect, then this again, the data depends upon the various growth stages. When you again, different platforms can be considered. Data models, they take into account the information. Further, they analyze it, study the patterns, and gives us the output. And again, this vagueness, which algorithm to use. This is life cycle of, again, we have already discussed it. So business case evaluation can be again linked into defining site and ambient conditions. When we are going to the field, we define the conditions of the field. We see which crop is there and all the other things. Like data identification, again integration of sensor with drones. Then data acquisition and filtering can be accounting into setting of flight parameters, calibration, uploading the mission. I'll be discussing in detail in further slides. And further, data extraction and validation can come under the category of image processing and analysis. Then data visualization, image pre-processing and analysis. Further utilization of analysis result is resultant imagery. In the first image, you can see the hexacopter integrated with the hyperspectral sensor, which is in the range of 400 to 1000 nanometers, having 269 bands, and the spatial resolution depends upon the altitude you are flying the drone at. So the second image corresponds to the data acquisition in wheat field uh, some time back. So this is the flow of UAV data acquisition and processing. So when I am talking about defining the site and ambient conditions, one day prior or before taking the data into the field, what you can do is you can just go and see the growth parameters of your crops. Is there any cloud coverage or not? What are the exposure settings? So all those things need to be kept in mind in order to see whether you'll be able to take the data or not. If the wind speed is quite high, so you need to manage the speed of the drone also, and the altitude at which you want to fly the drone. So all these things should be decided prior to fly your drone. Then integrating the sensor with drones, as we have already discussed in the previous sessions that there are multiple types of sensors. So the current sensors that we are using is RGB sensors, 3 bands, multispectral sensors, 5 bands, that is RGB, red edge, and near infrared IR band. Hyperspectral, I mentioned the details already, thermal, and LiDAR. Currently, we are not using LiDAR, we are using some other techniques in order to ortho rectify our image. So we are not using LiDAR as of now. So you can see the images of RGB sensor that we are flying. The hyperspectral sensor we have already shown, and this multispectral sensors and thermal sensor are linked integrated with this drone already. So mission planning, we need to keep certain things in mind, that what should be the flight speed. For example, if the wind speed is high, we need to maintain some flight speed. So for normal agricultural application that we are following is the speed of the drone, we are keeping it between 3 meter per second to 5 meter per second. This we have decided by a lot of other experience and a lot of flight hours. So further, the ground resolution, or again we know about the pixel, the clear pixel which it could identify, the sensor could identify. So again, it depends upon your application. If you want a very high resolution imagery, you can go for 3 centimeters. Normally we are keeping it varying it between 3 to 5 centimeters, because this is a very high spatial resolution data we are working with. Then again, front overlap and side overlap. So front overlap is also known as end lap, and also the side overlap is known as lateral overlap. So front overlap is recommended for this sensor, that is 1%, and the side overlap is 40% in order to get your image right. So whenever it is mosaicing your image or generating the orthomosaic, which is geographically correct, so it is taking as 40%, so which is the recommended one. For multispectral, we are taking as 75%. So again, overshoot in meters is the distance that you give your sensor to stabilize further before it enters the polygon to take the image. And again, these are some other specific specifications. And then again, when we are taking this polygon, fixing a big polygon, this automatically generated scan lines are coming. So drone starts from here. You need to give a takeoff position, you need to give a landing position also. So whenever you are flying it, so there are multiple software will make you aware about the mission planning. So for the hyperspectral, we are using the one which was supplied with the sensor itself. So that is UGCS software we are using for that. So that is the licensed version that we are using. And for other software are also there which are freely available. Pix4D is the licensed one which we are again using for mission planning. So then we come up to setting up the flight parameters. Most of the parameters I have discussed in the previous slide. So what should be the maximum altitude it should go, and if the emergency return altitude, what should be there. So in in case of any problem, for example, the battery discharge is there and the drone is going beyond our line of sight, so it would immediately return to home. So that is RTH, whichever would be the takeoff position, drone will be automatically returning in, or if it detects some of the other objects, or it is moving beyond the line of sight, so it would come down to this height, that is 50 meters or 30 meters, that whatever you specify. In India, according to this new drone policy, the maximum height is 120 meters that we can go up to. And also, apart from this, we cannot fly in the regions near high security areas such as airports or things like that. So we need to keep that in mind before designing our field acquisition map, or before doing the field planning. So it's very important to calibrate your sensor, which is a very important part. In case of RGB sensor, the calibration of RGB sensor is very important. This is done in this image. We can see we are taking the sensor and we're just pointing out to the screens on the black dots which are highlighted here also. So in order to see wherever we are positioning the camera, it's seeing the right object. Then again, IMU calibration is very important. Why it is important? In order to maintain the stability of drone with respect to the altitude, with respect to the angular velocity. So there are certain parameters which Dr. Ravi and Sahu would be discussing tomorrow with regard to the calibration also. And then compass calibration is also important. Why? Because we need to align the north of drone with the Earth's north pole. So therefore, compass calibration is important. Then calibrating the multispectral sensor. Multispectral sensor is mounted further on his drone, and it is shown with the white panel in order to calibrate it, so that when the maximum light is entering the sensor, how it is behaving. And also, further, using Hyperspect software, we are doing the calibration for the hyperspectral sensor. So here we fix certain parameters such as exposure. In a bright sunny day, we are normally keeping the exposure of 6 to 8. And also, further, if the cloud coverage is there, we don't prefer to take data at that time, but still by increasing the exposure, we can take the data. But since our experience says that we should avoid those days, because the image does not turns out to be well. It sometimes has noisy or salt and pepper noise in it. Then uploading the mission to drone is very necessary. So all the information related to latitude and longitude is now imparted to the drone in order to tell the drone where to start the camera or to take the image. So it would not be taking the image in the overshoot areas, because it would be stabilizing itself. When it enters the polygon or the area of interest you want to take into account, then drone would be the camera would be started. So this is uploading the mission to drone. So you need to wait, and once it is done, this is the takeoff position and the landing position. It needs to see, and these arrows define the direction of the drone, and also the altitude. Also, you can vary from the parameters that we set during the time of mission plan. Further, the image can be we can start, no problem. Anyway. Okay, so acquiring the image again. So depending upon the flight plan, whatever you have planned for it, you can now there are two modes in your in the drone. The first one is manual, and the other one is the automatic one. There are multiple other also, but we are doing it hyperspectral sensor. We are using these two. So in manual mode, what you can do is, the benefit is you can control the drone as your wish. But in automated mode, what it actually does is, the all power is in hands of software and also the controller. So the flight controller. So in that, what we can do is, we can start it, and automatically it would cover the trajectory that you have told to. Then after you have acquired the data, the most important step is to transfer the data. So there are two things. One is the live streaming one. If you are taking the data and it is of very it is occupying very less storage, that it can be streamed again. But for hyperspectral data, it cannot be done in this way, because it occupies a lot of space. Therefore, there is an onboard storage which is present inside the sensor, uh, and we can store the data. And using the same software from head wall, we can transfer the files and further analyze it. So image pre-processing and analysis is done using Spectral View software. We'll be discussing about the software, the details of the parameters that we have substituted in, and all this on Monday and Tuesday. So the same team which we have provided, which they have provided the sensor to us, they'll be discussing about all of these parameters. They'll be giving the live demo of this, and they'll be making you aware about the pre-processing steps also, which are followed using their software. So image pre-processing and analysis is, you can open your raw image, which is in terms of the digital numbers or raw files. Then after that, you can convert it into radiance. Further, the radiance image can be converted into reflectance. When you're going from DN numbers to radiance, this software demands a dark reference file. Dark reference file means when you have completely covered the lens from the lens cover, and when no light is entering, technically no light is entering into the camera, that needs to be subtracted out of it. And that file is used when you are going from, or when you are transforming your DN values to the radiance. And further, after radiance, in order to calculate the reflectance, you require the white reference file. So you can see a tarp here, which I have also showed you while calibration. So this tarp is of 2 meter by 2 meter. It's a square. So not only it is used for ortho rectification, that means your image to give the latitudes and longitudes correctly. So it is also used to generate the white reference file, which is used for converting the radiance values into the reflectance values. Here you can see the range of the reflectance values, because they vary between 0 to 1. So it would be automatically converted in the software, and the reflectance image, which you can see from here, and see the variations in the image which was having DN values, further the radiance values and the reflectance values. It appears to be high in contrast as compared to the other two images. So this image, you can save in TIFF, you can save in byte sequential format, and you can use other software to analyze it. Normally what we are doing is, we are having uh, some of the uh, some of the software which we are using, such as NV, and the other software that we are using for coding is again Python and R for prediction capabilities. So after all of these general steps that I have told you, we get the resultant imagery. So this is the RGB imagery that we have acquired from drone. This is the RGB sensor. This is the multispectral imagery we have acquired from the multispectral sensor mounted on drone. And again, this is the 5-band imagery, and this is high in spatial resolution because the altitude was quite low. And again, this is the hyperspectral imagery, that is of 269 bands, and this can be seen here. So these are the spectral library plots, or when you are clicking on a certain pixel, pixel itself is a spectral representation of that attribute. So these are all there are different nitrogen treatments with respect to this field. Therefore, there are a lot of spectral signatures generated with this respect. Maybe in visible region, we are not able to identify it, but in near infrared region, we are able to uniquely identify it. So this is the beauty of hyperspectral image, that you are able to identify each spectral signature uniquely out of it. And also, again, I mentioned the range that was between 4,000 to 1,000, sorry, 400 to 1,000 nanometers. And you can see these values. These are the reflectance converted values, which I showed in the previous slide also. So all these concepts would be covered in detail now, and every session would be belonging to one of this topic. So tomorrow we'll be discussing about the concepts of hyperspectral remote sensing with respect to airborne data, and the principles which are involved in it, the sensors that we are using it. So this is just to give you the brief idea about the workshop. And these are the images. You will be seeing the live demo also by tomorrow. So if there is any doubt with in this regard, you may ask. So these images are related to some of the data that we have acquired in the field. So this is our whole team, and we are actually readily flying this again and again. So there is a lot of data which lies there to explore. Therefore, the big data analytics is a very important component of airborne hyperspectral category.
We have a lot of invested a lot of energy during by seeing that presentation and watching that presentation, we can see how much it can be explained better. Thank you so much, Salini. And from our side and from your side also, and with this, the today program is over, and tomorrow we will meet at 9:45. But for that you have to come by 9:30 at least. And the first presentation with our co-director, Dr. Ravi Narayan Sahu sir, and he will tell about the UAV remote sensing. And after that, there is a practical session that will be the live demonstration and how we acquire the data, what we have learned today. This lecture session we have seen, and tomorrow we will see the live demonstration of the data acquisition through RGB, thermal, and multispectral sensors. With that, and thereafter, after lunch session, there will be EC team are going to visit us, and they will tell about the drone to map. There is software in ArcGIS, and there is a INVI software that will be demonstrated tomorrow. With that, the session is for today class. It is over. Thank you very much for your active participation, and I think 100% attendance from the offline participants. And although I am requesting the online participants that to get the certificate, it is mandatory to attend all the classes, all the sessions. Otherwise, certificate, it will be very difficult to us to provide you the certificate. The certificate for online participant will be e-certificate, and for the offline participant, we will give him the hard copy of that certificate with a group photographs. That is okay. Okay. Now you enjoy.
Anything related to stay or any problem till now? So I think Sunny has made my job easy for tomorrow. Because tomorrow is
Sir?
1.5 hours.
Sir, from this side, online participant also.
So she has covered not only the data analytics, also sensors and how the flow chart with respect to acquisitions, starting from hyperspectral, multispectral, and RGB. So many of those slides I'll be removing from my portion. So tomorrow we'll talk about the basics of the drone, how it works, what are the basic principles behind it, and of course sensors will be there. Then more related to practical we'll talk about. So how to go for a mission planning, what are the questions we should follow. So we have SOPs for that. There is a manual for that, and I think you will get in your pen drive. We have a pen drive which giving all the documents. You don't need to write down anything. So we have prepared a lecture material manual for this training, and also a SOP drone remote sensing manual we have already published. That also we are going to give you. Whatever the document publications we have, we are going to put in that. So maybe after 3-4 days, we are going to share with you that pen drive. And so tomorrow by 9:30, by 9, we should be here so that we can start the class by 9:40. We are very tight scheduled tomorrow onwards because most of the classes are on practical, and practical takes its own time. When you go to the field, you have to work out and integrate, fly. There will be some technical hitch and all those things. So again, there will be video recording for online participants to see live streaming in the field itself, how the drone is flying, what are the mission planning, all those things. So I'll be taking class with my team from the Big Data Analytics Remote Sensing Lab, with Salni, with Tarun, with Abhishek, Rajiv, all will be there. So I'll start with the basics, followed by Tarun and all those. They will show the mission planning. My pilot is there, Pratim. So how mission planning can be done using commercial software and also free domain software available before going to the field, because in field you can't see in the screen. So then we'll capture the data and come back with the different cameras we have. We have a RGB, we have multispectral, we have thermal, hyperspectral we are holding, because with slowly we'll go with to the hyperspectral. So tomorrow is what. Once you capture the data, then afternoon what we'll do is we'll go for processing. Again, the processing will be done by again two softwares. The ISRI India, the ArcGIS supplier, Environmental System Research Institute USA. Those team are coming and showing us mission planning to data analytics. Then we have our own software. Maybe next day that class is going to be taken up. So how we have developed those pipelines and how we can do the data analytics with respect to all those data captured. So that's why the flow diagram with respect to the schedule, you can see it will make a story from the day one to the day end. So if at all you have any query, always you can WhatsApp anything, any problem with respect to your staying, anything, all we are available throughout. And again, I'm telling, sorry for the accommodations, shared accommodations, but IR is always having constraint with respect to the accommodations. Even if those who have come as a young faculties or researchers who are not supported by us, they have also requested us to accommodate in the guest house, but with great difficulty, we could get one or two. But again, we'll try our best to make you comfortable. So with this, I think we should call the day and see you tomorrow morning, and enjoy. Enjoy the winter in Delhi, and that too in IRE campus. Thank you. The inside temperature is 2 degrees minus outside. So whatever weather forecast, you can -2 it. Suppose it's 3 degrees, then inside will be 1 degree. So be careful. Thank you. Thank you.